So I think that we can go directly to the first presentation. If you do have some questions or some other points to highlight, please do it. Otherwise, we go directly to the first presentation by Professor Zuccaro. Maybe you, Petros, as the coordinator, would like to say a few words as well.
Yes, actually very few. I want to thank the organizers, obviously, the University of Thessaloniki and the University from Naples for putting this virtual training together. Also, I want to thank everybody who is attending. It's quite a few. I see there are 20 participants, so I'm looking forward to a very interesting presentation. My only request is that for the presenters, you introduce yourselves, because some of the people may not be regulars for the ISTOS project and they may not know you. So it would be a good idea if you first introduce yourself and before the present. That's it.
Okay. So can you hear me?
Yes.
Yes.
Okay. So I'm going to share my screen. Okay, you should see now my screen.
Yes.
Let's reduce this at icons. And this is presentation mode. Okay, so good morning, everybody. My name is Giulio Zuccaro. I teach solid and structural mechanics at University of Naples. And my interest on the response of structure under the action of geohazard has been then, has taken me to work on the evaluation of the assessment of the damage at the territorial scale induced by natural hazard. That is basically the title of my presentation. At the moment, I lead the Center of Competence of the National Civil Protection Department in Italy. And my activity is basically to define the impact assessment due to volcanic potential eruption in Campania region. You know that Naples is in the middle of 3 volcanoes, active volcanoes. One is Vesuvius, Campi Flegrei is another one, the caldera Campi Flegrei, and the third is Ischia. And apart from that, our activity involved many other risks, like hydrogeological impact, like inundation, or even erosion on the coastal or coastal flood, landslide, and seismic, of course. These allow us to, and recently even the climate change impact, like heat waves and urban flooding. These allow us to have even a multi-risk vision that we will discuss later in the second part of my presentation. What I will present is basically a series of definition and of methodology, in order that we will understand one each other now on without any doubt, and by sharing terminology, meanings, methodology of assessment, and models. What you see here is the classical disaster management cycle. There are many versions of these, and someone of the experts that are listening, like Professor Pitilakis, could say, I would add this, I would add that. But of course, this is something that has been discussed in many contexts of the scientific community. And but this is the basic one, let's say. So you can start from any of these bullets, but if you start, for instance, from disaster, then you have the response of the disaster, that is the activity during the disaster. So search and rescue, emergency operation, and so on. And to do that, of course, you should organize a good civil protection, but the civil protection need desperately the function of the scientific support, because the science can give us a lot of information about what is vulnerable, what is not vulnerable, what the safety check, for instance, of the building after an earthquake, or the safety of a slope, of a basin, or whatever. So, I mean, it's important always that the scientific community will support the decision of the civil protection during the response. Then, obviously, there is the recovery, because after the first response, that is the phase in which you save people trapped under the ruin of a building collapsed, or you care people that remain without houses and foods. But after that, you have to recover. That is, in a way, all the activity following the disaster. So temporary houses, processing and claims, processing and grants, long-term medical care and counseling. I mean, all the activity that tend to rehabilitate the area to the normal life. That obviously last months or sometimes many, many years. Then, of course, there is the mitigation. You don't want that this damage will occur again. Okay, so you have to organize, plan to support them, or measure to support the mitigation of the potential damage in case of possible future earthquakes or volcanic eruption or inundation or whatever. And to do that, obviously, you have to decide the budget that you want to spend, the measure that you want to assume, and this is a very engineering phase, but not only engineered phase, because even the optimal dislocation of the resources on the territory could reduce the impact. So mitigation is not just only the retrofitting of the building or infrastructure or whatever, but could be even the optimization of the resources already available in order to give a prompt response and reduce the impact. Then the preparedness, again, that is exactly what we were discussing. So preparedness plans or civil protection plan, emergency exercise, training, warning system, and so on. So I want to be prepared for the possible event that is coming. Coming back to mitigation, I miss to say that another important element to take into account, apart of the building code, zoning, vulnerability analysis, or whatever, it's the retrofitting measure is the public education. This is very important because more and more the social response to the potential damage by event expected, that in a word is resilience, is more and more present in all our activities and give us a potential information for mitigation and and reduction of damage. Okay, so a few words about terminology of risk and scenario. Risk is the probability that a determined level of damage to element at risk, like people, building, infrastructure, can cause caused by natural events occurring in a given period of time and in a certain geographic area. The risk should be understood as a cumulative assessment which assess the potential total damage generated by all potential events. So in a way, risk is something that is normalized with the coefficient between 0 and 1, because a risk is all the cumulative damage that living in a place you can perform. Living in Naples, I can be kicked by an earthquake, volcanic eruption, heat waves, urban flooding, and so on. So in theory, or if you want to consider multi-risk, but if you consider just one risk, you could consider that being in Naples, you could be kicked by an earthquake, and then after some years by another earthquakes, and so on, because an earthquake is coming from the Mediterranean Sea, another one from Irpinia, Apennine, and another one from Sicily, and so on. So in this case, risk is the cumulative assessment of potential damage that you can experiment living in a place. What's the difference of scenario? The difference from scenario is that scenario is just one of these events. So the scenario is the quantitative evaluation of one single event. Like if you make one extraction of all the possible events, you decide the intensity of this and the probability of occurrence of these events, and you evaluate the impact assessment for that event. So in this case, you evaluate the quantitative impact. That means number of collapse, number of dead, number of injuries, so it's not anymore a heuristic comparison like the risk between one zone and another zone, living in Rome or living in Naples, which are the different risks living in those different towns. Okay, no, this is something else. Scenario is, in case in Naples, you perform an earthquake of intensity 8, what is the quantity of damage expected? Number of collapse, number of damage, okay. And of course, these two parameters can be, these two results, risk and scenario analysis, can be evaluated through 3 parameters that I suppose you already know very well. So just few words, just for the completeness of my presentation. Hazard is the probability of occurrence of all possible events, of a single event of a given magnitude in a specific area and in a specific time period. Exposure is the probability of extension, quantity and quality of different anthropic elements which characterize the examined area, whose conditions and the functions can be damaged, altered, or destroyed by natural specific events. While vulnerability is the probability that the element at risk considered, building, people, activity, or what else, show a level of damage according to the input of hazard, and so the intensity performed. These two formulas are the one that we use to evaluate risks and scenarios. The main difference, as you see, is on hazard, that in the first one is an integration of an hazard, while in the second one is just one single hazard choice. So in the first one is the integration of all the possible earthquakes that in the next 25 years or 100 years, I can experiment in Naples. In the second one, the scenario, I choose just one earthquake, for instance, intensity 8, and I evaluate, obviously, as I said before, which is the quantity of damage expected. The analysis level make a difference, of course. I can work at the territorial scale or at the punctual scale, so at the scale of the buildings. The scale of the buildings is obviously something that I can do even with the deterministic methods and analysis that drive me to understand which kind of buildings can resist or not to specific actions. While if I want to make a territorial analysis, of course, I can work either using, as we'll see later, observation of the previous earthquakes, and so the behavior of the categories of the buildings, specific categories of the buildings, under specific excitation, specific input or intensity, magnitude, acceleration, or whatever, and grouping the behavior of a class of the building that have performed the similar response, I can build up some curves that will be called vulnerability curves, we will show later, that actually describe the behavior of a category of building similar that I can group it. How can I evaluate the response of the building? I can do it in different way. I can do it either by using observational damage of the previous earthquakes, I already said before, or by calculating a simplified model and building up a virtual statistic with the Monte Carlo method or whatever in order to evaluate the vulnerability function. We'll say a few words later on. Which is the methodological approach? The methodological approach foreseen these different phases. First of all, you have to decide which is the minimum reference unit of analysis. You want to study a town, you want to study a quarter, you want to study a cell of a grid. What is the minimal reference unit? Of course, according different reference unit of analysis, you can decide which is the best approach for the analysis. Because of course, if you want to give one single evaluation of the whole town, because your goal is to compare different towns, of course, you have to decide for a more general approach. While if you want to compare different cells of a grid that you overlap to the territory with the dimension of 250 meters by 250 meters, this obviously require different methods and different, more detailed evaluation. Okay, then you need a damage scale. Even in this bullet phase, the damage scale has to be something that could be compared with other analysis around the world, and is essential to evaluate the damage at the territorial scale. Then the hazard, the vulnerability and exposure, of which we already said a few words in the introduction, just to explain the meaning of these words. Then impact, the case studies, and finally, potential mitigation measure to adapt. So the minimum reference unit depends by the scale of analysis, as we already said. At international scale, for instance, the minimum reference unit could be a country, Italy and Greece. Which country is more risky in terms of earthquakes or volcanic eruption or whatever? Or macro region, Campania region and Sardinia, or Campania region and the Sicilian region, and so on. At the national scale, in this case, is the municipality. So Naples, Rome, Catania, Palermo, Milan, Turin. I want to make a comparison of the earthquake risk because, for instance, I want to distribute money. And this has been done actually in the past. I have a budget and I want to decide where is more important and more, what is the priority of the distribution of money. Or at the local scale, can be taken as a sub-municipal area, for instance, in the census area, if there is a census in the country. In Italy we have, and in many other countries of European community exist the census and the census area. Or at the level of a cell contained in a mesh, in a grid, 500 by 500 meters, or even smaller, 250 by 250, according to the reliability of the input data available, of course. In case of risk analysis for infrastructures, that is a specific element at risk that has a particular peculiarities, the most appropriate minimum reference unit may be the segment of the network between two intersection of nodes that is generally called link. In order to evaluate the section where, of course, the damage and the reduction of functionality and the influence of the reduction of functionality of the link in the connection between different cells of the same grid, where there are, for instance, different functions: hospital, civil protection, deposit of ambulances, fire brigades, and so on. Okay, so of course, the different minimum reference unit influence the damage on element exposure. For instance, for people, you can measure the damage as the number of people damaged, NRU. Building, the number of buildings, lifelines, the number of links interrupted, economy, monetary damage for economy sector, environment, effect, consequences to different environment component, and so on. So just to say, to be careful that the methodological approach can be standardized. And obviously this is something that we encourage. But of course, case by case, the measure of damage can change. There is not exist the black box where you can push the button and the result come out. No, like a joker. No, this is not possible. You have always to evaluate case by case. Damage scale for generic element exposure, you can see here, no damage, the zero, then total collapse D5. This is generally used for buildings, but you can add to this even reactivation times. That means then money and loss of functionality, for instance. The same damage scale for people, absence of health effect, or for instance, health effect irreversible or partially disabling, and so on. And for building, it could be even applied, for instance, for landslide or pyroclastic flow, you can even detail much more the damage, because when you say slight damage, you can say if negligible damage to structural element, to infill panel, breakthrough of large and weak openings. So you can include a more complete description when a particular kind of hazard, like landslide or pyroclastic flow, oblige you to take in consideration other elements, not just only the structure, because we all know that for landslide, for instance, or for pyroclastic flow, the main structure could still stand, but all the opening, all the infill panel could be blow up and collapse. And I mean, in the case of pyroclastic flow, this could cause the burning of the house. So the loss at the end of the house in any case. So it's important, this kind of the detail. Damage scale for lifelines, the same. You can consider even the quantity of the link interrupt, even the function lost, and the time of the rehabilitation required for this kind of interruption. When you speak about hazard, you can obviously have a different, I mean, first of all, you can have an approach, statistical approach, by considering the event of the past, so that you can define through geographical distribution of the event magnitude with reference to assigned probability of accident in a given time interval called return period. This work can be done, in this case, also at the national scale, and we in almost all of the European countries, we have a map of probability of accidents. For instance, the one that is shown here is 10% probability of accident in 50 years map of the peak ground acceleration, or even at the local scale for specific study, like the one that you see in Campi Flegrei on the right side. Vulnerability curves is a probability that the element at risk exposure grouped in a class, in family, in category of building that performs in the response similarly. So vulnerability is a probability that this element at risk could suffer injury, damage, or other change of status quo following impact from one or more events. Okay, obviously the behaviors of each vulnerability class can be assessed through typical vulnerability curves, and they express a probability that a given probability class exceed a certain level of damage given by a level of hazard magnitude. Okay, this is a generic curves that show what we intend for vulnerability. The exposure in the risk analysis, as we said, is the quantitative and qualitative and the extension of different elements that characterize the examined area. Of course, we have to choose which are the characteristics of these elements. For instance, in the case of building, one of the most common way to characterize the peculiarity of the buildings that gives a response, stronger or weaker, is the combination of vertical structure and horizontal structure. By vertical and horizontal structure, we assign class A, B, C, D, according to the response that we expected. Okay? These can be classified, of course, building by building, but you can imagine that if you want to do this for all the building in a country is impossible, sometimes even in a town. So we take advantage from the census that gives us some generic information that generally are wrong, are not precise, because you see the census is done not by expert technician and engineer that could say, this is masonry, this is reinforced concrete of such and such characteristic, but give us a basic uniform information. So we are used to correct the census information on age, vertical material, masonry or reinforced concrete, the number of floors, and a few other parameters that the census provide, with some data collected, some samples of data collected on the site, on the spot. And so we calibrate, but everybody do like this, calibrate a sort of statistical calibration to correct the census data, and evaluating the error of the census data, then you can have a distribution of A, B, C, D building typology a bit more reliable. This can be done with even some forms. Some of those has been developed by the Italian Center of Competence, Lewis, for the civil protection, in order to evaluate more quickly the kind of ordinary building characteristics. Other factors are important to evaluate the impact, and other factors influence the exposure. That is, for instance, the time distribution of occupants, so the occupation of the people in Italy by working day and holidays, according to different way of life, style of life. Indoors, time that people are indoors, outdoors, and in different places, or moving, traveling, and so on. And in the working day and the holidays time. This because since we know that more than 75% of the people affected by an earthquake, for instance, but not only earthquakes, even other kind of hazards, are more than 75% of the building kicked by the earthquakes. So the casualties are because of the building collapse. And that means that obviously, if we are in the building or outdoor of the in or out of the building, make a difference. That's why these kind of analysis are important. So as is important, the possible tourist index that region by region increment the number of population in a town and inside the door. So seismic impact case, the intensity or magnitude or acceleration, and these are the conversion tables between intensity and magnitude, Italian seismic classification, as I already mentioned before, the norms, the code has incremented a lot the municipality that have obligation of taking into account the expectation of earthquakes. You see on the right side the map, the assessment, the seismic hazard for each zone with the acceleration expected. And of course, then there is a vulnerability of the buildings. I already showed before a possible combination of vertical and horizontal structures, so different classification of family of buildings. And for each of that, you can build up vulnerability curves. How can we evaluate these vulnerability curves? As I said, we have two possible methodological approach. One by observational damage, observational approach. So we observe earthquakes after earthquakes, the damage occurred in the past, and we can then make a statistic by combining these three elements: intensity, building typology, and damage. And we create the curves. Or if we don't have enough data, and this happens, for instance, for landslides or for volcanic eruption, because we don't have so many observed damage by this kind of event, we can work with the mechanical approach, with the limited state analysis and whatever we want to use in order to evaluate vulnerability curves. The casualties is being defined in the previous study, as I said, by using all the data of the number of dead, injuries, and homeless from previous earthquakes, taking into account that according to the damage level, you can evaluate some percentage of injuries or dead according to the vulnerability class, as is synthesized in the table in the bottom of the slides. Yeah, of course, there are some simple relation that quantify this kind of. This is an example that we do in Irpinia earthquakes, and show you the model with the number of injuries, that dead, collapse in a grid of 500 meters by 500 meters. This is another application for the earthquakes of L'Aquila. The intensity on the upside and the impact on building on the down part of the slide. So as impact on people, that was the previous one was impact on building. This is impact on people, and this is impact on links. Landslide, safe land. This was an important European project. We shared this experience with Professor Pitilakis. This was very exciting. Simple math to evaluate the impact of the building. This the dynamic pressure on the buildings, and in this case, the hazard can be evaluated by considering the slope and the basing and invasion area. And this is the Castellammare application of the model. So this is all the zonation of the basin and the slope. And according to that, you can evaluate the height, the volume, minimum and maximum of material mobilized, the length, and so on, all the parameters of hazard. And by using a Monte Carlo simulation, you can make a lot of analysis on a very simplified model of building typology and derive the curves. The same for vulnerability of people. This can be done using even other kind of data available in literature. This comes from Finlay and al. In 1999, where you can find some parameters to evaluate the impact on people. So hazard, vulnerability, buildings vulnerability, and damage. On volcanic hazard, very quickly, because I see that I am going long of 2 minutes and I want to close in very short times. The hazard that we have evaluated as cases are the volcanic earthquakes, ashfall, and pyroclastic flow. These are volcanic earthquakes and ashfall, pyroclastic flow, dynamic pressure, and temperature. All these hazard evaluation come from INGV, National Institute of Volcanology, that is our partner, is another center of competence. And vulnerability is derived by us, but derived either by calculated vulnerability or by test on site at the collapse. I'm sorry for this noise, but there is someone upstairs that is making some very fastidious noise. Fortunately, I'm going to finish. Vulnerability of buildings. So you, in this case, require to make another kind of vulnerability class according to the characteristic that you want to consider. In this case, for instance, it's important even the kind of windows of the opening for pyroclastic flow, as I mentioned at the beginning of my presentation. And this is the different scenario according to temperature, dynamic pressure, fire, and so on. The same for ashfall. The same for ashfall. And finally, just one word for climate change, because another application using the same methodology. So these are just only examples that I want to show just quickly to say that the same methodology can be applied to earthquake, landslide, volcanic eruption, but even to climate change. What you see here is an European project that we closed just last year, Clarity, that has as a goal the evaluation of the impact on a grid overimposed to a town. In this case, we apply to the Naples for heat waves and the pluvial flooding. This is the model of hazard, exposure, and vulnerability that gives the idea of the affection to the people. Element at risk are people, obviously, and economics. Here is a sun map that show you the impact at the sanitary system and the energy consumed. And this has been very useful to the municipality of Naples that include this evaluation in the urban planning of the town. Mitigation, obviously mitigation means that you have to consider the cost. This is the volcanic case of all the phases, and consider some different technological option, make this assumption, and to understand which is the best. So that means that you have to do cost-benefit assessment by using multi-risk mitigation potential analysis, energy improved potential, urban regeneration potential, and so on. And so you can combine risk and mitigation in the parametric design that allow you to combine disaster risk reduction, climate change adaptation in one single whole approach, of which perhaps we will discuss later. Thank you very much for your attention. I'm sorry if I've been a bit longer of 5 minutes.
Thank you, Giulio. A fantastic work, and yes, there are a lot of things that could be available to the people that are attending this this virtual training. I suppose that all this material will be available in the site, and
yes, of course.
with a lot of references as well. If somebody would like to go in more detail, for example, in the Clarity projects or in the results of Clarity projects, etc., we could come directly to you in order to ask more information.
Yeah, I upload the presentation, and I will add a consistent reference to these issues.
Excellent. I think it was very, very useful from many points of view. Quite a dance, but really very, very interesting. With a lot of small numbers, how you make it, all this?
In 20 years. Don't worry, I'm 20, 25 years of work synthesized in half an hour.
Yes, it's very interesting. It's very interesting because it is always very difficult to come up with some results that could be used in practice. And as I remember from almost 20 years from now, your work, you always try to do it. And this is not an easy work, yes.
No, that's right. Thanks.
If there is no specific question to Professor Zuccaro, we can continue with the other presentations. Do you have any question, please?
Hello, good morning. Actually, I have one. Hello to everyone.
Yes.
Good morning, Professor.
Good
I
morning.
have a question about the evaluation of the damage level. What is the exact criterion in order to categorize a damage level of a structural element? Is the length of the crack, is the width, or something else?
No, I tell you, everything starts, as Professor Pitilakis knows very well, from experience of the damage level classification of the macroseismic scale. Because you see, the mother of all the analysis, of all the risk analysis, is the earthquakes. Because since the beginning, 40 years ago, people started in evaluation of earthquake risk assessment at the territorial scale, working on the base of the macroseismic scale. In the macroseismic scale, there is a scale that goes on 6 levels, adding D0, no damage, D5, total collapse, and are described very well, are described in slight damage, moderate damage, heavy damage, partial collapse, total collapse. These 5 classes, actually, all are the risk analysis that in the year came after, because hydrogeological came after, volcanic came after, everything. Try to take into account this description, but not because it, well, on some reason is even good, because slight, moderate, intermediate, partial, total sound well as a distribution. But even because has been always underneath clear that even if we were not able to do, and perhaps even now we are not so able to do very well, sooner or later, all these analyses could be combined. You see what I mean? So in a way, the classification of damage in 5 classes of damage is something that is generally accepted. Sometimes it's grouped, 0, 1, D0, D1, D2, D3, D4, D5. That has a sense, because D0, D1 is more or less no damage. D2, D3 is an intermediate damage, D4, D5 is partial and total collapse, and it has a sense, but no more than that. And so there is not a rule, but is, you see, a reasonable way to approach this.
Okay. But how we know if our damage, the building damage, is on slight or moderate level of damage?
That's what I was saying, that in the macroseismic scale for earthquakes is very well described. It's very well described, and it's described conceptually. So for instance, D0 is D0, no damage. D1 is damage that not affect the structure. So for instance, chimneys or any other plasters, any other element that are non-structures. And so D0, D1 could be combined in a way. Then D2 is slight damage, and this is described the level of the cracks, the kind of, you see what I mean? D3 is an heavy damage where the cracks is more important, is more than 1 centimeter. And then partial collapse is partial collapse. It's just a part of the structure that collapsed. Total collapse is, you see, is a total collapse.
Okay, I understand. Yeah, thank you very much.
Just to complement this macro scale approach, there is no unanimously accepted figures and numbers for the damage states. If you go in HASOS or in Europe, in GEM or in other parts, in Synergy, etc., we are proposing, they are proposing, everybody is proposing. There is a certain consensus. There is a certain consensus about let's say, the story drift limits in one case or the other, but still there is some subjectivity behind this. Anyway, there is some levels which is accepted by everybody. We follow this and we see the effects of these assumptions. But still there is an assumption behind, because it depends very much on the quality of the structure. So it's not straightforward and a single decision independently of the quality of the structure. But you have a lot of damage states estimates, and you can use the one that you believe is the most appropriate for your case, plus the macroseismic approach that has been described by Professor Zuccaro very well. So this is the question, the answer.
Yeah. Then there is, you see, there are people believe always that it's a good idea to invent against the will. So anytime, so starting from the past, someone could decide, okay, there is already a classification, we can take that. No, but anyone want to, but sometimes is, as I said, it's necessary, and okay, it's necessary. But I mean, yes, Professor Pitilakis described very well the situation. Yeah.
Okay, so thank you very much. We go to the next presentation. Evie, it's up to you. Make your presentation first and then make the rest.
Thank you. And thank you also, Professor Zuccaro, for your very comprehensive introduction to the risk assessment of natural hazards. I am Evie Riga. I am a civil engineer. I am a member of the teaching staff in the civil engineering department of Aristotle University of Thessaloniki. My main interests are in geotechnical earthquake engineering and mostly on site effects, seismic hazard and seismic risk assessment at urban scale. So in this first virtual training of ISTOS that we are very happy to organize with the University of Napoli, I will make two presentations, which will be the first one on the new European seismic hazard model and the second on the new European seismic risk model that were released a couple of months ago. So I am going to make a presentation of the two models and also give some examples of some applications that we have done here in Aristotle University using these very new and very interesting models. And I will also guide you through the portals of the two services, which are very interesting and provide very useful information and very useful data sets for everyone who wants to go on with such kind of analysis. So I will share my screen and start with the first presentation. Can you all see my screen?
Yes.
Yes, okay.
Yes.
Thank you. Okay, so we will start with the presentation of the European Seismic Hazard Model, which is abbreviated as ESHM 20. 20 stands for the year 2020, that it was first supposed to be released. It was finally released in 2021, but the name stayed the same. And as I said, some applications mainly in Greece, and also provide some guidance with useful data that can be used for applications mainly in Cyprus. At the bottom of the slide, you can see the main the names of the core team that developed the ESHM 20, and they are from many different institutions along Europe. Many other researchers participated in the development of the model with providing data or with their participations in some seminars which took place along the years that this model was developed. And of course, in the presentation, I will provide many different references which refer to the different components of ESHM 20, so that anyone who is more interested in getting into more detail can go to these references and get much more information. These two models, the ESHM-20 for the hazard and the ESRM-20 for the risk, are a result of a very important European research program that ended in 2020. This was the SERA project. You can see in this slide all the different institutions that participated in the project. The Aristotle University was one of these institutions. But although the ESHM-20 was developed in SERA project, it is not something new. Many efforts to produce a European seismic hazard model have started from many years ago. For example, in 2002, there was the Sesame project, which produced the first, which made the first attempt to produce a European seismic hazard map. And when we say European hazard map, the main thing that we have to keep in mind is that these European maps are harmonized. This means that there are no significant differences between the hazard estimates at the borders of the different countries. And this was the goal that all these different projects tried to achieve. So we had the Sesame project in 2002, and then in 2013 we had the development of the ESHM-13 European hazard map and model, which was the result of the SHARE project. And now in 2020, we have the ESHM-20, which is actually an update of the 2013 model, but with many, many new data and many new approaches that were incorporated in this model. On the other hand, for the risk, the 2020 model is the first European seismic risk model that has ever been produced. And this is something that makes it very interesting and very innovative. So here is a few words about the previous and the current projects that led to the development of these models. So the SERA project started in 2017, and it included two work packages which were particularly focused on the development of the ESHM-20 and ESRM-20. The SERA project ended in May of 2020. At that time, the model was not finalized, so it continued to be developed under the umbrella of the European Facilities for Earthquake Hazard and Risk Assessment, VFR, and it was finally released in December 2021. The European seismic risk model, the ESRM-20, is in fact going to be included in the global earthquake model, which is well known as GEM, so that the European part of the global earthquake model is updated using these latest developments. Let's go on and see some of the main features of the new hazard model, ESHM-20. As we said, it is an update of the previous model that was published in 2013, and it was developed within the SERA project. One of the main advancements compared to the previous model, it is that it was developed with a significant increase of earthquake data and information across Europe. It is a uniform seismic hazard model, and this means that it is fully harmonized across national borders to cover the whole Euro-Mediterranean region. This model served also as an input for the first European seismic risk model, ESRM-20. And one very important feature of ESHM-20 was the interaction of the team that developed ESHM-20 with the working groups that are in charge of the development of the revised version of the Eurocodes, and more specifically Eurocode 8. So a very important milestone that is relevant to ESHM-20 is that in October, in last October 2021, there was a decision by this committee that is in charge of the development of the new Eurocode 8 that some results of ESHM-20 will be included as an annex in the next version of the Eurocode 8 as an acceptable representation of the seismic hazard in Europe for a term period of 500 years. So ESHM 20 will be, in fact, a part of the new Eurocode 8, and it will be used as a basis for any country that wants to adopt this seismic hazard model. And perhaps the most important feature of ESHM 20 as well as ESRM 20 is that all the data and all the products and all the input datasets are openly released with a specific license that allows anyone who wants to use them, adapt them, and further develop them. This is something which is really very important. We'll start with a small overview of the ESHM 20 model. First, we will see some things about the input datasets that were developed in the framework of the development of ESHM 20. Then we will see the seismogenic source models and the ground motion models that are adopted by the model. And finally, some few slides on the hazard integration and the results that are provided by ESHM 20. We start with the main input data sets. The first data set that we present here is EPICA. It is the European Pre-Instrumental Earthquake Catalog, which includes historical earthquakes between 1000 and approximately 1900. This is in fact an update of the previous catalog that was developed by Studi et al. In the framework of the SHARE project, which resulted in the first version of the European Seismic Hazard Model in 2013. So this is a database. We see here in this slide all the earthquakes that are included in this database, in the EPICA database. It has around 5,700 earthquakes with an intensity which is higher than 5 or a magnitude which is higher than 4. And 64% of the earthquakes that are included in this database are supported by macroseismic data, while the vast majority of these earthquakes are reported in regional catalogs. So all this data from the different catalogs were harmonized and were compiled in this database. You can see here at the bottom of the slide the reference of this historical catalog, where you can go and find more details about this dataset. Another dataset that was compiled within ESHM 20 is the instrumental European Mediterranean Earthquake Catalog, which is called EMEC. It is again an update of the previous version that was developed in the framework of the SHARE project. It covers the period between 1900 and 2014, which means that it has new data after 2006 that were not included in the previous catalog that was used in the SHARE project. It has around 56,000 events with magnitude greater than 3.5 for the period after 1900. And the majority of the new data that were included in this database were a result that there was a drop in the minimum magnitude that was considered for Southern Europe. In SHARE, this was 4. Now in ESHM 20, it's 3.5. So we included more events in this instrumental European catalog. You can see, of course, here the reference for this new catalog, and here in the figure we can see how these events are distributed across Europe, and the distribution based also on the depth of the earthquakes. Now, these two catalogs that were developed, the one with the instrumental earthquakes and the other with the historical earthquakes, were combined to form this unified earthquake catalog, which consists of both the instrumental catalog and the pre-instrumental catalog. So this is the unified catalog, which has an additional 8 years since 2006 with respect to the previous catalog that was compiled within the SHARE project. And in this table, we can see a summary of the characteristics of this unified earthquake catalog, and also a comparison between the ESHM20 catalog and the ESHM13 catalog. So here we can see how many more events have been included and what the differences in the different parameters are. Another very important data set that was compiled for the development of ESHM20 is the European Fault Source Model, which is abbreviated as EFSM20. Again, this is an update of the previous database of faults that was developed in 2013 by the team of Basile et al. in INGV. There are two main categories of seismogenic faults that are considered. The first one refers to the crustal faults, and the second one refers to the subduction zones. In this map, we can see how where the faults of this European database are located. With the different colors, we can see the faults that were provided by different institutions. The information was provided by different institutions. And here with these letters, we can see also the different subduction systems that are included, which are the Gibraltar Arc, the Calabrian Arc, the Hellenic Arc, and the Cyprus Arc. Here we have zoomed a bit more in the area which covers Greece, and we see which are the faults that are included in this European fault database. All this data, as I will show you in the following, are open to everyone, so everyone can access and see all the details of these faults. Regarding the subduction zones are complex systems where different types of potential earthquake sources exist. The assumption that the earthquakes occurring in the upper plate of a subduction zone are dealt with by the crustal fault model was adapted, and the subduction model was designed to prospectively assess the slab interface seismicity and the intra-slab seismicity. Here we can see the geometry that was finally adopted for the Hellenic Arc and for the Cyprus Arc, and which were in fact very recently revisited in the framework of a tsunami hazard project by Basile et al. Another data set which is very important for the development of the new ground motion model that is adopted in ESHM20 is the ground motion dataset, which is in fact based on the European strong motion flat file by Lanzano et al. In 2019. So this is a flat file which contains over 20,000 strong motion spectra. This means that it is almost an order of magnitude increase compared to the previous version of this flat file, which was the resource file that was used for the SHARE project. And the greatest increase in data is between the magnitudes 4 and 5. We can see here in this figure how the different records are distributed based on the Joyner-Boer distance, and we can see how the events are distributed based on the magnitude and based on the distance, and we can see also how we can see the distribution between the number of stations and the number of records. The reference for this database is given at the bottom of the slide. And here is a map where we see all the ground motions that are included in the ESM flat file. We can see also with the yellow triangles the sites, and with the different circles of the different colors, we can see the locations of the events, and they are categorized according to their depth. Now, all these shape files that were developed for the input data sets can be accessed through this link. And if you click on this link, you will be driven to this repository when you can see that you can download all these different data sets. And if you are familiar with GIS software like QGIS, you can upload them in such a program and you can view them. For example, here I have zoomed a bit in Cyprus so that we can see, for example, with the red lines, the faults that are included in the faulted database, while with the little green dots, we can see the events that are included in the unified catalog. All these data are available for the whole Europe, and anyone can have access to this data. We're moving to the seismogenic source model. This was built upon the foundation of ESHM 13, but it was enhanced with all the new data that was available through the work that was done for ESHM 20. So this model consists of 4 distinct source models, so that the spatial and temporal uncertainty of the earthquake rate forecast across the whole Europe can be captured. So we have the area source models, which is assumed to be the pan-European consensus model. We have the active faults, which are combined with the background smooth seismicity, which is mainly used for regions where there are not many faults. We also have the subduction zones, which include the Hellenic, the Cyprian, the Calabrian, and the Gibraltar arcs. And we have the non-subducting deep seismicity sources, as is the one in Vrancea in Romania, as well in some parts in southern Iberia Peninsula. So the seismogenic source model mainly consists of the combination of the area sources, which are shown in the figure on the left, and the active faults combined with the background seismicity, which is shown in the figure on the right. As we said before, it's an update of the previous model of ESHM 13. So the area sources were improved compared to the model of the ESHM 13. These area sources describe regions of homogeneous seismicity and are classified as shallow, crustal, volcanic, subduction in slab, and deep seismicity. The most important part of this work is that the cross-border harmonization was ensured. For example, if there were some areas which were close to the national borders, where there were differences between the countries that are bordering, these differences were harmonized so that there are no differences across the borders. And the activity rates of each individual area sources were finally estimated. Here we can see a figure where we see the final rates that were calculated for the area sources. These figures are all taken from the technical report that is available for the ESHM 20. Now, regarding the active faults and the background seismicity, again, this was based on the European fault source model of 2020. There was a smooth seismicity assigned based on the tectonic supersonation, while in the vicinity of active faults, the background smooth seismicity is complementary to the seismic productivity together with the faults. But in the region where there are no faults, the smooth seismicity is in fact an alternative to the area source model that was presented in the previous slides. Regarding the maximum magnitude, there were different assumptions made based on the different source model. Here we can see a map where we can see the different maximum magnitudes that were considered for different parts of Europe. Some criteria that were adopted for the definition of the maximum magnitude have to do with some macro regions that were developed following a regionalization which is based on the tectonics. In some other cases, the maximum magnitudes were obtained from the Unified Earthquake Catalog or from the faults. And this is the logic tree that was finally constructed to incorporate all the different models, the seismogenic source models. So there are two main branches. The one has to do with the area source model, and the other has to do with the active faults plus the smooth seismicity. These models have the same weighting factor. But of course, if someone wants to try some different weighting factors, this is something that could be tried. Regarding the ground motion model, this was based on the European strong motion flat file that was presented earlier. Here, the approach of a scaled backbone ground motion model was adopted, which means that there are not different ground motion models that are combined in a logic tree with different weighting factors. On the contrary, there is a single ground motion model which was developed in the framework of the project, and this is calibrated to take into account the different uncertainties that are expected in the ground motion as a result of the limited knowledge of the seismological properties in the region. Here we can see an example of this backbone ground motion model and how there are different weighting factors assigned to take into account the different uncertainties which have to do with the attenuation and the stress parametry. And this is the equation of the ground motion model by Kota et al., which was finally used in the ESHM 20. Here we can see how this ground motion model is implemented for the calculations. And here we can see some comparisons between the SERA, the ESHM 20 ground motion model, which is shown here with the different gray lines. And we can see how this compares to some well-known ground motion predictions that were used in the previous version of the model, in the ESHM 13 version of the model. So we can see that there are some differences which are higher for higher values of epicentral of distances. So as we move to higher distances, we have some higher differences between the new and the old ground motion models, and these mainly refer to the small periods. For higher periods than 0.1, we can see that there are not so many differences. Moving to the hazard computation, all these data that were presented previously are combined in appropriate input files so that this calculation, the hazard calculation, can be done in the OpenQuake software. This is an open source community-driven software that is used both for the hazard and for the risk calculation. For the ESHM 20, the classical probabilistic seismic hazard calculator was used. This means that the classical probabilistic analysis was performed to get these results. And the model is divided into different computational regions. So we have the main Europe, Iceland, and the Oceanic Islands. The different input files that are needed to run these calculations are these 4 files that are shown here. We have an XML file for the source model, we have the configuration file, and we have the ground motion logic tree and the source model logic tree, which are both the XML type files. All these input files are available. You can access them from this link. If you click on this link, you will be taken to this kind of environment where you can download all these input files, and you can reproduce all the results of ESHM20, provided that you have installed OpenQuake and you become familiar with using it. Here we can see the grid, the computational grid that was used for the seismic hazard calculation of ESHM20. There is a total number of around 98,000 grid points. So for each one of these grid points, you can get all the ESHM20 output. Let's see now which are the main results that are given by ESHM20. The ESHM20 results depict time-independent earthquake ground shaking exceedance levels for a uniform rock site condition of VS30 greater than 800 meters per second. So all the results that are provided by ESHM20 refer to this reference site condition, which is the same that is adopted by Eurocode 8 for soil class A, which is the rock class in EC8. So for this specific site condition, the main results of ESHM20 are more than 500 hazard maps for specified intensity measures. So we have, apart from PGA, all the spectral values for periods in the range of 0 to 0.05 to 5 seconds, and for 5 mean return periods starting from 50 years and going up to 5,000 years. For each one of the computational sites that we showed in a previous slide, we can get the hazard curves for the mean, the median, and 4 quantile values, 5th, 16th, 84th, and 95th. And these are available for all the above mentioned intensity measures. For each computational site, we can also get the uniform hazard spectra, again, for all the percentiles and for all the different mean return periods. And soon, a disaggregation of the hazard results will be available perhaps in the following year. All these results are available online at this portal, at the FAIR portal, which we will see in detail in a couple of minutes. But let's first take a look at some examples of these results. Here we can see the European maps, which provide the PGA, the peak ground acceleration values based on the new seismic hazard model. Here we can see the mean values. Here we can see the median values, and at the bottom figures we have the 16th percentile and the 84th percentile. So these maps are available. These maps refer to the 500 return period, but these maps are available for all the different return periods that are included in ESHM20, but also for all the different intensity measures, which are in fact the spectral acceleration at different spectral periods. Here we can see a comparison between the new model, the ESHM20 model, and the previous model that was produced in 2013. But if we want to have a better comparison, it's better to look at this figure where we present the difference for the peak ground acceleration for the 500 years return period between the new model and the previous model. So the regions which are red, means that the new model gives higher values than the previous model, while for the regions that are blue, which as we can see are the vast majority of the European continent. So for the blue means that the new model gives smaller values than the previous model. So we can see that with this new hazard model, the hazard estimates for Europe are reduced for the majority of Europe compared to the ESHM13 that was the previous available European seismic hazard model. However, both maps have a similar spatial pattern. and some increased values are observed in parts of Romania, Albania, Greece, Western Turkey, Southern Spain, and Southern Portugal, while for the other parts, we can see that the new model is reduced compared to the previous one. The differences that are observed between the models are likely caused by the updated seismogenic sources and the new backbone ground motion model that was used in this new model. Some other results that are available are the uniform hazard spectra for different return periods. Here we can see for 4 different locations, L'Aquila in Italy, the island of Rhodes in Greece, the city of Cologne in Germany, and Lisbon in Portugal. We can see the uniform hazard spectra with the new model for different quantile values. And also we can see how this is compared to the previous ESHM 13 model. Some other results that are available, as we said, are the hazard curves, which show us for the different return periods that are considered how the expected peak ground acceleration or other intensity measures are distributed. Here we can see the ESHM 20 hazard curve for L'Aquila, and on the right hand for Rhodes in Greece. Again, different quantile values are provided in these figures and are compared with the ESHM 13 estimates. An important thing, a very important thing that is related to ESHM 20 is that, as we said in the beginning, it will be somehow adopted by the new version of Eurocode 8. And how is this going to be? How is this going to happen? The new Eurocode 8, the revised version of the Eurocode 8, will have a significant difference in the way that the elastic response spectrum is estimated. So, so far we had one single parameter that was used to anchor the elastic response spectrum based on the hazard estimates, and this was the peak ground acceleration. So if we had the information for the peak ground acceleration at a specific point from a seismic hazard analysis or from a seismic code, we were able, using the equations of Eurocode 8, to estimate and draw the elastic response spectrum. In the new version of the Eurocode 8, we will have 2 different hazard parameters instead of 1. And these 2 parameters will be the ones called S alpha and S beta. The S alpha refers to the maximum response spectral acceleration. So it's actually the value at the plateau, at the constant spectral acceleration part of the spectrum. This is closely related to PGA, and in case that there is no other information, it will be calculated. The PGA will be calculated from S alpha by dividing S alpha with a coefficient of 2.5. The second parameter, which is tau beta, refers to the spectral acceleration at a spectral period of 1 second. So if we go to the spectral period of 1 second, the value of the elastic response spectrum at this period is S beta. So for the new Eurocode 8, for each point where we want to calculate, to estimate the respective elastic response spectrum, we will need to know the values of these 2 parameters. So ESHM 20 calculated maps for these 2 parameters, for S alpha and S beta, for the whole of Europe, and always referring to rock site conditions for a mean return period of 500 years, which is the most commonly adopted return period in seismic codes. So the main contribution of ESHM 20 for the new version of Eurocode 8 are these 2 maps that we will see in the following slide. Now, as we said, these two values refer to the rock site conditions, and these will need to be properly amplified using amplification factors. So there will be two instead of one amplification factors, F alpha and F beta, which will amplify S alpha for rock and S beta for rock. Another thing that is new in the new Eurocode 8 is the way that the seismic classes are defined, and the way that these amplification factors are estimated, which for the first time in Eurocode 8 are intensity dependent, which means that for higher levels of seismic hazard, we will have lower values of site amplification factors, so that the different phenomena associated with soil nonlinearity can be taken into account. Here we see the way that the site classes will be defined in the new Eurocode 8. We can see that apart from the VS velocity, which is more or less the VS30 that we know from the previous version of the code, there will be a new parameter which refers to the depth of the seismic bedrock. It is the depth where the VS profile starts to get values higher than 800 meters per second. So for each one of these site classes, there are two amplification factors, F alpha and F beta, which are calculated with some equations that take into account the intensity of the ground motion. And here we can see some other parameters that are needed for the definition of the elastic response spectra. These are the two maps that I was referring to previously. That refer to the way that ESHM20 contributes to the new version of the Eurocode 8. So here we can see for the whole Europe, the S alpha median map, referring always to the 500-year return period and for rock site conditions, while here on the right we can see the respective map for S beta. Similar maps have been produced for the mean value. So here is the mean S alpha map and here is the mean S beta map. However, in Eurocode 8, most probably the median maps will be incorporated as an informative annex. And now I will show you some examples of the portal where you can access all the different data sets and results. The link, the address of the portal is the one shown here. It's hazard.fr.org. This is related only to the hazard component. In the next presentation, we will show the one related to the risk component of the European model. So apart from ESHM20, through this portal, you can access also the previous model, which is ESHM13, as well some other regional models that are included. But if you want to access the ESHM20 main elements, you will have to click on this point right here. And if you want to access the whole repository of all the data, you will have to click on this link that I show here. So let's go and take a look at the portal. I think I have to share again my screen. Okay, we'll share the whole screen now. Can you see my browser?
Yes.
Yes. Okay, thank you. So here is the main portal of FAIR, which has links for both the hazard and the risk component. If we are interested in the hazard, we will click here, access to earthquake hazard data. So we are taken to this environment that I showed you also in the slide. If we click on these two links, we can get into the different data sets for the ESHM20. But if we want to actually view some results, we can quickly click on these 3 points where we can get access to the hazard spectra, the hazard curves, and the hazard maps. So let's click for example, the hazard spectra. And this page is loading. So here we can see a map of Europe with the S alpha at 5 Hertz for the 500-year return period. But here we can set all the different parameters that we want to get the results that we want. So here first we have to define the point that we are interested in. Let's use some coordinates for Cyprus. Here I have the coordinates of 3 main cities in Cyprus. So let's take, for example, Nicosia. The longitude is this, and the latitude is this. So I click on use, and here we have a symbol on the map which shows us where is the point that we have selected. Now we move to the selection of the hazard model. We have the option to either use the new, the ESHM20, or the previous ESHM13, or the EME 2014, which was a model that was referring to the Euro-Mediterranean region. So I will click on the ESHM20. Next, we have to decide which parameter we want. Here we have only the alpha, as we are on the uniform hazard spectra component. Here we select the return period. Let's go for the 500-year return period, which is similar to this probability of exceedance. Only a rock site condition is available, so we select rock. And here we select the aggregation type if we want the mean or a fractile. Let's go for the mean. We can also choose to compare the uniform hazard spectrum that we will get from this page with a design spectrum. So, for example, we can select a magnitude greater than 5.5, which refers to the type 1 Eurocode 8 spectrum. And let's select also a ground motion value. I don't know if someone can tell us what is the PGA for Nicosia based on the hazard map. Otherwise, I will just insert 0.2.
It's okay.
And add design spectrum. So here, what we see is with the blue line, we get the uniform hazard spectrum based on the new model, and with the black line, we get the design spectrum based on the current Eurocode 8. We can also insert multiple uniform hazard spectra on the same page. For example, we can choose to plot along with the ESHM20, the ESHM13. So if we click on add hazard model, we can here select also the ESHM13 so that we can compare the spectra for the two models. And we can also choose to add some more fractiles. So let's say I also add here the median value, which is the 15th percentile. Okay, sorry. So now we have, apart from the previous two curves, we also have two new curves which refer to the ESHM13. These are these two dotted lines. The one is the mean and the other one is the median. So we can do different kind of selections here and do any kind of comparison that we want. If we go back to this first screen, there is a second module which is for the hazard curves. So it works in a similar way as the one for the hazard spectra. Again, we choose the point. Let's go for Limassol now. So here is the longitude. And here is the latitude. Again, we choose the model that we want. We choose the intensity measure that we want. Since this is a hazard curve, it will be a different curve for different intensity measures. I will select S alpha for the 1 second, which is the parameter used also in the new Eurocode 8. All the results are for log, and let's see the mean. So here is the hazard curve. We can see for different probability of exceedance in 50 years how the S alpha for the 1 second is varied. For example, if we go to the 10% probability of exceedance in 50 years, which is the one used for the design, we'll go here to 0.1. And we'll see that the S alpha value for this return period, it's somewhere between 0.1 and 0.2 G. And finally, there is another option here. It's for the hazard maps. Here, you could either choose to download the whole map for the whole Europe. So if you just give here some coordinates, and again, select the model and the intensity measure and the probability of exceedance. Let's say a different here and the mean value. If you click on download map, you will get the results for the whole Europe. So if you click download map, you get the map which refers to these selections that you have done for the whole Europe. So these are the three main tools that are available on this platform. Here you can access the details of the models. And if you click here, this is perhaps one of the most interesting parts. You are taken to the GitLab where all the input data are stored. For example, let's go to ESHM20 as we are now on the hazard part of the presentation. We will see here that in the documentation folder, you can download these technical reports, which describes in a very, very detailed way all the different components of the model. If you click on these input shape files, you can download all the shape files that are related to the individual data sets that have been developed within ESHM20. So, for example, if you download and open them in QGIS, you will see this kind of image that I showed you earlier. So here we can see for Cyprus, as I said, the faults. Sorry. Or you can see the locations of the events that are included in the Unified Earthquake Catalog, or you can also see the zonation that is used for the model. So these are, for example, the different area sources that are combined in this region, which is around Cyprus. And finally, here in this folder, which is called OQ Computational, you can download all the different input files that are needed by OpenQuake to run the analysis yourself, or run a different analysis which is focused more on a region of your interest, and in fact reproduce or get some kind of different results using all the input files that have been made available through ESHM20. So this was a short walkthrough on the platform. I think that we're a bit past our time. Do you think we should make a break, or shall I continue for a couple of more minutes to finish with this?
No, I think that you should finish and then make the break. Okay,
so a few more things. Some applications that we have done using the results of ESHM20. one important application that is currently in progress is that we are trying to use the results of the new ESSM20 model to propose a new seismic hazard zonation map for Greece. This is a first draft of what we are considering. So instead of the 3 zones that are currently in the EAC code, we propose 4 different zonations. This zonation was based mainly on the S-alpha parameter. And here you can see the proposed parameters for S-alpha and for S-vita. Of course, these values refer always to rock site conditions, so they will be properly amplified to take into consideration the site effects. Another application refers to some major industrial sites in Greece. So what we did here was we gathered some information about some sites where important industrial facilities are located, and we tried to compare the hazard based on ESSM20 with the hazard based on the current version of the seismic codes in Greece. To take the site conditions into account, we use the VS30 mosaic model that is available from USGS, which is mainly based on the slope and is not always very effective, but in any case, it is an option if you don't have available data for the whole region of interest. And here we plot, we show the median peak ground acceleration values for these specific sites for the 500 years and for the 2000 and the 500 years, which is a return period which is very relevant for industrial facilities. For each one of these, we did the specific calculations and comparisons. For example, here for the Aspropyrgos refinery close to Athens, we compare the uniform hazard spectra from ESSM20 for the different quantiles and the hazard curve for the mean and for the median. Here we compare the uniform hazard spectra for the same site for the 500 years and the 2000 and 500 years. And perhaps one of the most important things is that we compare the elastic response spectra based on the revised Eurocode 8 with what is currently valid based on the current version of Eurocode 8 and EAC. EAC is the Greek seismic code of 2000. So here we have the results for the reference rock site conditions. We can see that there are very important differences between EAC and the current between EAC and the current EC8 and the new version of Eurocode 8, which is shown here with the purple line. Of course, these are not computed with the final values of S-alpha and S-vita, so they will probably change. And here we can see how the things are changed if we take the local site conditions into account using the new amplification factors that are going to be included in the new version of the Eurocode 8. To get a more to get an overview of the results, we computed the ratio between the maximum acceleration based on the new Eurocode 8 divided by the maximum spectral acceleration based on the current EC8 and EAC. And here we can see that for most of the cases, these values are higher than 1, which means that based on the new Eurocode 8, the seismic hazard is higher than what is currently the case for the current codes. And this is something that perhaps we should be a little worried about, as these points refer to industrial facilities which are of specific importance in terms of safety in case that an earthquake strikes close to one of these locations. These are the applications that I had prepared for the hazard part. We will see some more applications which are related also to hazard in the second presentation, which is related more to risk. But for the risk, also the hazard component needs to be calculated first. So we will see some more in the next presentation. I don't know if there are any questions for now. Okay, perhaps we can have a short break and
For how long?
based on the agenda, the break was between 1:40 and 2. So maybe we can start at 10 past 2. I don't know.
Yes, 10 past 2. Okay.
Okay.
Okay. If we have questions, I think we have a lot. But if we have some very important one, we could raise our hands after the second presentation. Okay. Where is the risk assessment? Okay. Excellent, Evie. Thank you very much.
Thank you, Evie. Very interesting presentation. Very, very brilliant and full of things.
Thank you.
Thanks, Evie. Bye.
Yes.
It seems that you in Italy, you are not very satisfied of the results of SHM20. Not for theoretical or technical reasons, but mainly because in general, between us, there is a reduction of the values. And it is understandable that this is not so easy to be accepted easily. So there is an ongoing discussion about this. Of course, as Evie said, this is informal. It's not this table, this maps and the use of SHM20. The same stands for the site amplification factors.
Yeah.
There is a proposal. Personally, we have quite a lot of differences. Some of them have been accepted, for example, regarding the fundamental period for the classification of the sites, but some others not. In Greece, we will propose not only the zonation map that we have seen, which is for the moment a draft, but we are proposing also another way of estimating the amplification factors.
Okay.
It's more a tabular way of giving, similar to the way that is given in the USA code in HARP. We believe that it is much more practical and much easier to accept. And the classification is a little bit different as well, because SHM, this depth to the bedrock 800, it's very, very, very ambiguous in many cases in practice. And we think that a different way should be proposed. But anyway, this is something that could be accepted or not in the national annexes.
Yeah, of course.
It is the way that Eurocodes. So with this, I would like to give you some extra specification besides the way that Evie has presented.
Okay.
In Greece, we are satisfied.
Okay.
At least in our lab. And I would say not only, some discussions that we had, in particular within the engineering community, it seems that the results provided for the median values, not for the mean, for the median values, are on the good side.
Okay.
In Greece. A little bit higher in several cases, but they are, I believe that they are reasonable and they will be accepted somehow with some modifications eventually. But in Italy, there will be some problems, I believe, too, because you have done a nice work which has been published very recently. So probably there is also a diplomatic issue behind this objection. We have done it already. Why we have to think about it again? But it's
I don't know the detail of the work, but has been presented to the governmental commission of great risk, which I am part, a member, and I remember that there were a lot of remarks, and actually it looks a bit. I mean, is less conservative than it was before. That is the point.
Yes.
And this was clear. So even if you don't know the detail of how it's been derived, this is the first remarks that everybody does.
Yes.
This is basically the point.
This was the main reason behind the scientific remarks, etc. The main reason is that probably the results are a little bit lower than the previous one, which is in force now. And so, but anyway, we have participated in both SHARE and SERA, and it is really a fantastic work from the methodological point of view.
Yeah, that's true.
We may disagree in some points or in others. If the faults are like this, for example, in Cyprus, there were a lot of discussions about the faulting system, and in other parts of Europe, in Vrancea as well. But the methodological part is really the best that could
robust.
be.
Yes, it's robust. Yeah.
And very robust. But and so we will continue working with this and probably improving in some parts.
Yeah, I'll be happy to have more details from you and to discuss with Giulio.
Yes, if you want, and with Evi and Tassos and Stefania, we could provide all our ideas or our concerns, because we still have a lot of concerns.
Yeah, of course, this is normal.
And we try to find out the best way to propose something realistic and feasible.
Yeah, okay.
So this just to give some
let me know.
extra clarifications and specifications.
Okay, good.
Evi.
Okay, so we continue with the second presentation, which is on the European Seismic Risk Model, ESRM 20. So here, again, we see the main authors of ESRM 20, which are again from different main institutions, but there are many, many more that have contributed to the model. I tried to include as many references as I could in the presentation, but again, as for the hazard part, there is a very detailed technical report where anyone who is interested can get into all the details on the model. So let's start with the main features of ESRM 20. As I said in the previous presentation, this was the first time that there was an effort to produce a European seismic risk model, and it started in the European project SERA as a joint research activity. And after the end of SERA, it continued to be developed thanks to the support of ISTOS, RISE, and ISTOS Italia. The model has been developed in collaboration with the global earthquake model, and it has taken advantage of all the experience that was already in the global earthquake model for the risk modeling. Over 100 of researchers were involved in the project, as well as professionals, and there were many different workshops and meetings that took place through the development of the model. The model now covers residential, industrial, and commercial buildings, as well as their occupants in 44 European countries. So there are different exposure models that are developed for the residential, for the industrial, and for the commercial buildings. And hundreds of vulnerability models have been applied. Some of them were taken from previous works as the ones of the global earthquake model. Some others were specifically developed during SERA for ESRM 20. The risk model can be used to estimate economic losses in terms of replacement costs of structural, non-structural, and contents, and loss of life. The results are provided in terms of average annual losses at national and administration level 1, and losses for specific return periods which range from 50 to 1,000 years at national level. Again, all data and results are openly released, so anyone can have access to them. And the model will be maintained and further developed under the umbrella of the EFER consortium, which is the European Facilities for Earthquake Hazard and Risk. So the main components of VSRM 20. First, the most important component is perhaps the European Seismic Hazard Model, which serves as input for the estimation of the hazard component used for the risk modeling. So the seismogenic source model and the ground motion model logic trees that were developed in ISTOS 20 are used, but the main difference is that now for the risk modeling, the hazard that is needed as an input does not refer to the rock site condition of 800 meters per second, that was the case for the hazard model, but now the soil, the local site effects should be taken into account. For this, a European site amplification model was developed, which is a European model of proxy site data, which consists mainly of geology and topography, and these serve as input variables to the ground motion model so that all the local site conditions and the related site amplification phenomena can be considered. The third component is a European exposure model, which contains the distribution of the number, value, and occupants of buildings for 44 European countries. This model is divided into 3 different models for the residential, commercial, and industrial buildings, and all these buildings are classified according to different structural classes based on a very detailed taxonomy scheme that we will see in the following. And the fourth component is the vulnerability models, which consists of many different vulnerability functions for different vulnerability classes based on the adopted taxonomy scheme. And these provide losses, both economic and fatalities, for the different levels of ground shaking. We'll see now the different components in a bit more detail. For the European Seismic Hazard Model, we said a lot of things in the previous presentation. What we need to add here is that for the risk modeling, the hazard needed to be recomputed, taking into account the local site conditions and the site amplification. For this, some proxies were used to estimate the site response in ESRM 20, and these proxies are the topographic slope, the VS30 as it is inferred from the slope, and the geological unit. As a result of this work, there were some products that were released, and these refer to harmonized maps of geology, topography, and VS30 across Europe. And this is something that it is, in my opinion, very innovative. Some examples of these maps can be seen here of the European site amplification model. On the left-hand side, we can see the slope as it is calculated from the GEPCO 2014 digital elevation model. And on the right-hand side, we can see the VS30 as it is inferred from this slope model using the methodology by Walden Allen, which is probably known to some of you, which correlates VS30 mainly to the slope, to the topography, and also to the geology. So this is a VS30 model that was derived from this slope model. The European site amplification model also provides a composite map of geological unit at the European scale, which was developed using 3 existing maps: the geological map of the European project ProMine, the geological map of the One Geology Europe, and a bedrock geological map of Iceland, which is available from the Icelandic Institute of Natural History. Here we can see this unified geological map, which covers the whole Europe and which was developed based on these three existing maps. Now, the amplification model that was used in the European ground motion logic tree was based on both geology and topography, and it was implemented in the OpenQuake engine. One very important tool that was developed within ESRM20 is a specific Python tool which can be used to prepare input files for any given exposure model configuration. So if you want to do a specific risk analysis for a specific area, we can use this Python tool to prepare the appropriate site amplification model, which can be then inserted directly in OpenQuake and run the risk analysis. Moving to the European exposure model, models were developed for 44 countries. All these countries were, of course, covered by the hazard model. Here you can see a list of all the countries that are included in the exposure model. And new exposure models were developed for residential, commercial, and industrial buildings. And these were mainly based on data from the national census, as Professor Zuccaro also showed in his presentation. The data that were used were the ones that were at the highest available resolution. Of course, these are not, this may not be the same for all countries. So for some countries, maybe the models are a bit more detailed than for others. And these models use data that refer to dwellings, buildings, population, and workforce. All the source data that were used to produce these models, as well as the models, are all available in the same repository that we showed for the hazard. We will show again what is included there for the seismic risk part of the model. So different approaches were used to develop the exposure models. For the higher hazard countries, the public census data were used available at the highest administrative level. For Italy, Portugal, and Romania, a post-processed version of the census data was provided by local researchers. So these are maybe a bit more checked than the data that are taken directly from the census, which sometimes have many problems, as Professor Zuccaro also said. And for lower hazard or very small countries, some existing data were used as shown in the reference here. So here we can see a map which shows how the different exposure models in the different countries were developed based on what kind of data. Now, to better model the vulnerability of the reinforced concrete buildings, in the framework of the development of the exposure model, there was a mapping of the temporal and the spatial evolution of the seismic design across Europe. So 4 different categories were used, and these roughly include the buildings that have been built with no seismic design, the buildings that have been constructed with low code, moderate code, and high code. So in this figure here, we can see for the different countries in Europe, which are included in the model, what is the temporal evolution of the seismic design code. So for each country, we can see which periods correspond to which level of seismic design. So for Greece, for example, that we can see that up to 1959, we had no code, no seismic code. Then up to 1984, we had a low code. Up to 1995, a moderate code. And since 1995, we have a high level of seismic code. Here we can see a map for the whole Europe, which shows how the buildings in Europe are distributed to the different levels of design code. Here, in fact, we see the number of the low code buildings in the European exposure model and how the lateral force coefficients are distributed. So with the different colors, we can see the different levels of the lateral force coefficients. And similar maps are available for the other levels of code. This is an example for the moderate code buildings. Here you can see a nice GIF that was developed by the team of Helen Crowley, where we can see in the different parts of Europe how the lateral force coefficient is changing through the years, starting from 1910 and going up to 2000, I think. So some key features of the European exposure model. There are an estimated 145 million buildings in the European exposure model, and there is an estimated total replacement cost if we consider all kinds of costs, so structural, non-structural elements and contents. The total replacement cost is around 45 to 50 trillion euros, and 20% of this cost is attributed to industrial buildings, 20% to commercial buildings, and 60% is attributed to the residential buildings. In terms of material of construction, more than half of the buildings in Europe are made of masonry, 30% are concrete, and there's a 9% of wood, 4% of other materials. Regarding the design, the level of seismic design, 50% of the buildings have been seismically designed, and only 15% of this 15% has been designed with a high level of seismic code. So we can see that there are a lot of buildings in Europe which have no or a low level of seismic design. Here there are some figures that are available in the technical report, which show some of the main features of the exposure model. So on the left side, we can see the top 10 countries in number of buildings in Europe. So we can see that Germany, the United Kingdom, and France are the three countries which have the most buildings, while in terms of total replacement cost, the United Kingdom is the first country, followed by Germany and France. In this slide, we see a map which shows the exposure of the residential buildings at the highest resolution available from public data sources. So here we can see how in some regions the data were more densely available compared to other regions. And here we can see the buildings density, which is actually the number of buildings per square kilometer. So the darker blue, the color, it means that there is this is a region which has a higher building density compared to regions with not so bright blue colors. This is the case for the residential buildings. Here we can see the same kind of information for the commercial buildings. Again, the darker colors refer to regions with higher building density for commercial buildings. Now, the final exposure model contains, as we said, an estimated 143 million buildings. These buildings have an average of 460 million occupants over a typical 24-hour period, and a replacement cost which is in the order of 50 trillion euros. In these tables that are available in the technical report, we can see for each one of the countries of the European exposure model, the number of buildings in thousands, the number of occupants, and the replacement cost. With some colors are highlighted the countries which have the highest numbers of buildings or occupants. Here we can see for the countries which have the the majority of the buildings in Europe, what is the distribution between the three types, residential, industrial, and commercial buildings. As we said before, the majority of the buildings is in fact the residential buildings, but in some countries there are also a lot of commercial and industrial buildings, as for example in Germany and the United Kingdom. Here I extracted from some figures the respective numbers for Greece and for Cyprus. So we can see that in Greece we have 3.3 million buildings on average, while for Cyprus we have 280,000 a rough number of total buildings. Now, moving to the taxonomy that was used for the exposure model, here we can see using a simplified taxonomy, which has only the material, the height of the buildings and the code level. So we can see how the total buildings are distributed according to these very simplified taxonomies. These were not actually used for the vulnerability modeling. There was a much more detailed taxonomy that was adopted, and we will see it very soon. So based on this simplified taxonomy, we can see that the majority of the buildings in Europe are unreinforced masonry low-rise buildings. These are mainly residential buildings, and they are followed by concrete frames with infill panels, low-rise, low to moderate code, and by wood structures of low height. Now, moving to the vulnerability modeling, here, as I said before, there was a much more detailed taxonomy scheme that was adopted. This was used to define the vulnerability classes of the European buildings, and for each one of these classes, there was an appropriate vulnerability model that was used to estimate the respective vulnerability. So the main attributes that are used by this taxonomy scheme, it's actually a taxonomy scheme that was adopted by the global earthquake model. The main attributes are, first, the material. The material can be either reinforced concrete, reinforced masonry, confined masonry, unreinforced masonry, and so on, so that all different kinds of materials can be included. Regarding the lateral load resisting system, there is the dual frame wall system, the infilled frame, the load bearing wall, the moment frame, and the braced frame. Regarding the code level or ductility, the four different levels of seismic design that we showed previously were adopted. So we can either have no seismic design, low code level, moderate code level, or high code level. Regarding the height is categorized based on the number of stories. So we have different classes for the different number of stories. And finally, a new component that was used in this taxonomy is the lateral force coefficient, which is the fraction of the weight as was specified in the design codes, and is strongly related to the code level, and it is expressed usually in percent. So here we see an example of this taxonomy scheme that is adopted in ESRM 20. We can see that for each value of each attribute, there is a respective coding, and this coding makes it easier for someone to understand from this description what are the characteristics of a building that is categorized in a specific class of this scheme. So for example, if we see a building that is CR, we understand it's reinforced concrete. If it's L wall, we understand further that it has both wall and frames. If we see DUCL, we further understand that it has a low ductility, so it was probably built between 1960 and 1985 for Greece. And if we see that it is H2, we understand that it has two stories above ground. So this is an easy way to communicate and understand easily what each class, what kind of buildings each class includes. Now, the European vulnerability model of ESRM 20 is described in detail in this publication by Romao et al. 2021. And how was this developed? For many classes, the European vulnerability model includes the vulnerability models of the global earthquake model, which are the ones by Martins and Silva and in 2020. This is the case for all buildings except for reinforced concrete infill frames and moment frames, for which new vulnerability curves were developed by Romao et al., considering different number of stories, different code levels, and different values of lateral force coefficients. So for all these classes, the capacity curves were developed. Up to 300 capacity curves were simulated per class to account for the building-to-building variability. And finally, the vulnerability modelers toolkit by GEM, which is coded in Python, was used to develop the final vulnerability models for from the respective capacity curves. In this publication here, you can see all the details for all these vulnerability models. I cannot go to much detail right now. Just to say that the damage state thresholds that are used in this vulnerability model are defined based on the spectral displacement and on the spectral accelerations. While there are 4 different damage states that are considered in these vulnerability models, referring to slight damage, which is called DS1, moderate damage DS2, extensive damage DS3, and complete damage, which is called DS4. So for each one of these vulnerability classes, there are the respective vulnerability curves that provide the loss models for the economic loss and the fatality loss estimates. Now, the results or the outputs of ESRM 20 are maps of average annual loss for the residential, for the industrial, for the commercial, and for the total buildings. The average annual loss ratio and the 200-year return period loss at country level. And also there are maps of average annual loss, average annual loss ratio, and 200-year return period loss at administrative level 1 for the 44 countries. And there are data on the loss exceedance curves at country level and administration level 1. Some results of the ESRM 20 are given in the following slides. So here we can see a table which summarizes the average annual loss metrics for each country. So we have the average annual losses, the average annual loss ratio, which is the ratio of the losses divided by the total replacement cost for each country. And here we have the average annual losses in terms of loss of life. We can see, for example, that for Greece, the average annual losses are in the order of 600 million euros, while the average annual losses in terms of loss of lives are 33. For Cyprus, we can see that we have 114 million euros economic losses, and for loss of life for the average annual losses. Now, if we want to analyze a bit the results, we can see that the majority of the losses, both economic and loss of lives, are within the residential building stock, while the commercial and the industrial building stock have a large impact on the economic losses and not so much on the loss of life. The highest average annual loss was computed for Italy in terms of economic losses, while in terms of loss of life, the highest average annual loss was computed for Turkey. And this is probably related both to the high seismic hazard of the region, but also of the not so good construction quality that many buildings in Turkey we know have. In terms of relative losses, Turkey is at the top of the list, and it's closely followed by Albania, Cyprus, and Romania. Here we can see a figure which shows the average annual losses, its economic losses, so it's expressed in millions of euros for for the countries which have the highest average annual losses. So we can see that Italy is the first, followed by Turkey. For Greece, we have, as I said, 591 million euros, while for Cyprus this number is 114. And here are the countries which have the highest number of average annual losses in terms of loss of life. We see again that Turkey is the first, followed by Italy, Romania, and Greece with a number of 33. Here is a map. It's a map of the average annual economic loss for Europe at the administrative level 1. So it's one of the main risk outputs of ESRM 20. We can see with the different colors how these are translated into different values of average annual economic losses. Here we can see the map which shows the average annual loss of life across Europe. So again, the dark, the red colors show the areas which have the higher annual losses, as we said, for example, in Turkey, and the blue colors are the regions where the values are very, very small. Now, for the simplified taxonomy that we showed also previously, we can see that the highest number of economic losses and loss of life is associated with concrete frames which are of medium height and of low to moderate code. So from a table like this, we can get an insight on which kind of structures are the ones which contribute most to the European seismic risk. The second class are the unreinforced masonry low-rise, which are mainly residential buildings. So these two classes are the two classes that contribute more than 50% to the total annual losses for both the economic losses and for the loss of life. Here we can see some risk curves. In the same sense that we have the hazard curves, we can estimate the risk curves, which show us for different return periods how the losses are increased for higher return periods. Here we can see, for example, in the first figure, the three curves. For Italy is the green one, for Turkey is the blue one, and for Germany is the black one. We can see that, for example, for Germany, the loss curve is much lower than the respective curve for Italy. And here we can see some other results for other countries of Greece. Here we have included, for other countries of Europe, forgive me, here we have included Greece, and here we have included Cyprus. Now, like there is the hazard.fr.org portal, which provides access to the hazard data, we have the risk.fr.org portal, which provides interactive access to the model and to a number of services and tools for the main components of the model. We have access to the exposure models of all European countries for the residential, commercial, and industrial buildings, as well as their occupants. We have access to the vulnerability models for all the soil classes that were used for the taxonomy of the European buildings. We have access to the site response model at European scale, and we have access also to some earthquake scenario models that were used for the testing of the risk model. Okay, so here I have some snapshots from this for this platform. it is configured as it is shown here in this slide. If we click here, we access ESRM 20. If we click here, we access the technical report, which has a very detailed documentation of all the things that are included in the ESRM 20. Now, if we go to the first feature, which is ESRM 20, we will get a kind of of picture like this. So here we have 4 different options. We have the Access Seismic Risk Model, which gives access to the GitLab repository, where all the input files that are needed to run the analysis in OpenQuake are included. If we click on this little figure, we have access to a GeoViewer, which provides maps of pre-computed results with ESRM 20 as the maps that we showed in the presentation. If we click here, we have an access to some specific web services that have been developed. And if we click here, we have access to the tutorials. The same logic is followed for the other components. So for the exposure data, for the vulnerability data, for the site response data, and for the earthquake scenarios. If we click each one of these, we will have the same kind of picture when clicking each one of these points. We have the access to the relevant features. In fact, I have included in the presentation the link. So if I click here, for example, the access exposure data, but I don't know, do you see my screen or just the PowerPoint now?
I think the PowerPoint.
Okay, I should. Yes. Okay, I will share the whole screen now. Okay, so I was here. So clicking here, we are taken to this same GitLab repository that we showed before for the ESHM 20. So the main folder is a FAIR. ESHM 20 is the one that we showed in the previous presentation. So here there is a folder ESRM 20, and then ESRM 20 exposure, scenario test, site model, and vulnerability. If we go into the exposure, we can see here that there are different folders which contain both the input data that were used to construct the models, but also the models. And these are categorized differently in different folders for the commercial buildings, for the industrial buildings, and for the residential buildings. So, for example, if we go into this folder, which is the exposure models, we have the actual exposure models that were used in the calculations of ESRM 20. So, for example, if I want the exposure model for Cyprus, I can go here. I can see that there are 3 different files. This one is for the commercial buildings, this one is for the industrial buildings, and this one is for the residential buildings. So I can view the files, I can download them, and I can use them to run perhaps an analysis. Now it takes a bit time because these are a bit heavy files, so I will not proceed with this. There are similar folders, as I said, for the, for example, for the vulnerability. So if we, okay, why? So here in the vulnerability folder, I can actually have access to the capacity curves that were used to develop the vulnerability functions. And I also have access to these files. For example, this is the fragility functions that have been developed within ESRM 20. I can download the file and I can use these fragility functions for any kind of analysis that I would like to run. For example, we see here for all the different kind of typologies. There are the median values for the different damage states. So you have the median DS1, DS2, DS3, DS4, and of course the beta value that is needed to construct the vulnerability curves. I should highlight here something that I did not say before, that the vulnerability curves that are used in ESRM 20 do not use for all the different typologies the same intensity measure. So here we can see that there are different vulnerability models for PGA and for spectral values of 0.3 seconds, 0.6 seconds, and 1 second. And in the final tab, you can see which intensity measure was finally selected for each typology. So, for example, for a low building, PGA is used, while for a 10-story building, the S alpha value, the spectral value at 0.6 seconds is used. So going back to this repository, there are also all the data that were used for the site model. Here you can also have access to this site tool, which is a Python tool that can be used to produce for any kind of exposure the ESRM 20 site model that is needed for an analysis in OpenQuake. Here are a folder with the scenario tests that were used for the validation of the model. And finally, in the ESRM 20 folder, you can access all the input files that were actually used for the calculations. So in the configuration files folder, there are the input files that that can be used in OpenQuake to run the risk analysis. While in the other folders, there are the exposure models that are needed as input. And also, also the hazard input models that are used to run the hazard for the risk modeling. And in VS30, you can see there are included the site models that were used for each country in the development of ESRM 20. So the site model for Cyprus is, for example, available. In the vulnerability, you can see the models as they are needed for OpenQuake analysis. So you can download everything here that is needed to run, to duplicate the results, to reproduce the results, or to run any kind of analysis using these input data. And of course, apart from this repository, you can have access to the results of the model. For example, if we go into the explore seismic risk, we have these very nice maps that are available. For example, let's go to the European seismic risk model viewer per country level. We can see here, for example, the average annual economic losses for each country, or we can select the average annual loss of life. We can select anything that we want to view. And something which is very important, there is an option if you click here. And if you click on this QGIS project, you can download all this data as a project, and you can view it in QGIS and further use it for other applications. Okay, so we saw some of these things. These are some results from the scenarios that they did in ESRM 20 to validate the model. You can access them from the platform. And finally, have some applications from some analysis, seismic risk analysis that we have performed with the new models. I don't know how we are in terms of time.
Very short time available.
Okay.
Try to do it
Okay. Okay. So first, I would like to show some examples of two scenario analysis that we did in OpenQuake to validate the models. So here, these are not probabilistic risk analysis, but these are scenario risk analysis, which means that we simulated two of the most important earthquakes that have occurred in Greece. This is the 1978 earthquake in Thessaloniki and the 1999 earthquake in Athens. And what we did was we simulated these two events in OpenQuake, and we used the ESRM20 vulnerability model to see if the estimated losses are well correlated with the actual observed losses. So we did this for these two events, making some assumptions for the VS30 using the slope approach by USGS. And what is probably most important is to show you the comparisons. So I will go to these two tables that I have in this slide. So here we see how the damage that we estimated with the ESRM20, we can see two different columns here. This is using a rupture model approach, and this is using directly the shake map that is available for this event. So we can see how these estimated damages are compared to the actual damages as were reported after the event. So we can say that there is a quite good correlation between the estimated and the observed damages. Of course, many assumptions were made here, for example, to associate the different damage states to the color tagging that is used for the characterization of a building after an earthquake. However, we can see that the results are more or less okay, and a slightly worse result was obtained for the Athens earthquake. Of course, we should say here that for the Athens earthquake, the exposure model is not as detailed as was for the Thessaloniki earthquake, so this might be one of the reasons for these larger differences. We have further used this model to test how the site modeling affects the results of the seismic risk at urban scale, and we have done this for the case of Thessaloniki in a recent publication that is currently under review. So we used different ways to model the site conditions, for example, using the results of the microzonation of Thessaloniki, or using directly the ESRM site model, or even using the amplification factors that are available by Eurocode 8 or by the classification scheme by Pitilakis et al. So we used different methods to model the site effects and the site amplification, and we try to see how this affects the hazard and the risk. So moving to some comparisons, we can see here how the peak ground acceleration is distributed in the study area of Thessaloniki using the four models. We can see that there are some quite important differentiations. However, when we move to the risk to the risk results, we can see that these differences are not so obvious in the estimated risk. So here we can see for the four different site models and thus hazard models that we used, how the damages are distributed across the different damage states. If we look at the total image, we can see that there are not that many discrepancies. However, if we go to local scale, for example, in the area of Kalamaria, where there are some specific soil types that amplify the ground motion to a higher degree based on the Pitilakis scheme. We can see that here the differences between, for example, this model and the other three models are quite significant. So at urban scale, maybe the site modeling is not so important, but if we go to a more local scale, some important discrepancies may occur. These are similar results for the damages now at census sector level, so at an even smaller detail, where we can see that these discrepancies are more evident. And we have made similar comparisons to see how the effect of the different vulnerability models affects the final results. So I will pass these slides and go here, where for the different case study of Thessaloniki, apart from the fragility curves and vulnerability curves by ESRM 20, we also use the ones by Kapos et al., which have been developed with a different way, using a hybrid approach, but are quite representative for Greece. And we see that the differences that we get with the two different vulnerability models can be quite important. One thing that is difficult here is how one can associate the damage states of the one vulnerability model with the damage states of the other. Here we use the loss index to do this correlation. Here we can see the comparison at municipality level. The figures in the upper part are with the ESRM 20 model, while the figures here are with the Kapos model. We can see that the Kapos model provides predicts higher damages than the one of ESRM 20. And this is also reflected in the economic losses, where we can see that with the Kapos vulnerability curves, the losses are higher compared to the ESRM 20 curves. And finally, we have recently performed an event-based seismic risk analysis for Thessaloniki. This is a completely probabilistic seismic risk analysis, where we can compute the expected losses for different return periods. We used the ESRM 20 models. This is from a paper that we have submitted to the European Conference of Earthquake Engineering that will take place in September. Here we can see some results for the hazard. So this is the mean PGA for different return periods. This is the S alpha at 1 second for different return periods. These are the hazard curves for some specific locations in Thessaloniki which have different site conditions, and we can see how these curves are distinguished. And finally, some results of the average annual damages. Here we show the percentage of buildings with greater than slight damage. And here we show the percentage of buildings with complete damage. These are all average annual damage maps. And similarly, some maps for the expected losses for the different return periods. And here we show the loss exceedance curve that is computed for Thessaloniki. Sorry for being so in such a rush in these last slides.
It is so complicated and so challenging topic that it was impossible to do it in a shorter time. Just one remark from my side before going to the next presentation, because I think that questions are rather difficult to be given now. Well, what is important to see from the two presentations of Evi is the tremendous capabilities of these two models. Of course, someone has to be familiarized with OpenQuake and with all these models, but once he will be able to manage them and to use them, he or she has a lot of capabilities of doing a lot of interesting things. And of course, will be able to judge and to think about the different kinds of uncertainties that are involved. What presented now by Evit is exactly this effort to understand a little bit where are the uncertainties, where the end user should focus his work in order to reduce these uncertainties and to propose as accurate as possible results. And in any case, we should know that the hazard issue is so complex and so variable that the truth is not existing. Actually, is a kind of estimation, and we try to be as close as possible to what should be expected. So you have seen, for example, with different fragility models and vulnerability models, that the cost between the one set of fragility curves and the other one, in terms of annual cost, repair cost, it was almost doubled, if I remember well, 4 million and 8 million. So this is something that we have always in mind. In any case, it is a very powerful tool, actually two tools, which I believe that will be used very much in the next years, in the future. And I'm sure that with a lot of people working with them, we will get much more maturity in using them and in getting good results. Just a general, let's say, a comment on these two tools. And thank you very much again, Evie.
You're welcome.
Any questions to clarify a couple of things?
Well, I would have a lot of questions, but this is not the case now. Actually, we should have another personal meeting with you and Evie to discuss this interesting presentation.
Yes.
I had no idea of the advancement of this project on this tool. It's exciting to see. Obviously, is I mean, very high level. I mean, it's quite ambitious, and so, as you said, the point is now to evaluate the uncertainty of the results, and there is a lot of work to do probably, and this is the best way to check the reliability of the results, because actually you are speaking about exposure of all Europe, and this is something that make me mad. I mean,
of course.
So
and a lot of differences, you know, a lot of differences between even in local scale, because for example, we are working with the safety of schools, and we have seen that the models of the vulnerability that are used in these models are not so accurate as the building specific fragility curves that we are producing numerically.
Yeah, okay, yeah.
And of course, not only numerically, but validated with measurements. I mean, with updating numerical models. So a lot of things should be done in several parts: modeling, hazard, exposure, damage states, intensity measures, amplification factors, soil models, etc., etc. But is already something very, very powerful and important on the table. This is
yeah, but this is the story. I mean, this is, well, the history, not the story. I mean, I am always in favor to this kind of things. I remember in 1985, with Andrew Coburn and Ron Spence, we built up perhaps one of the first model for risk assessment. I remember all my colleagues, engineering and architect, were just say, "Ah, this is rubbish. You never can say something like that." Yes. And I was conscious that was not the best, but was just the first attempt. And I was sure that in the future we could be much more confident in the results. And this is the same actually at European level. That is really ambitious goal, but that's brilliant work. Yeah.
And
Okay.
if I may add something last, since this is a virtual training, which is also attended by many, many students, I would like to highlight the open access and the transparency of all these input data sets and tools and software. It should be a great opportunity for students to use all this data to work on their master thesis or on their PhDs. I think it's amazing.
Yes, of course. And then if everybody use it and everybody work, everybody can implement and improve it. At the end, will be a good, a good final tool results. Yeah. Okay. Thank you, Eric.
Okay, so we go to the last part. It's your turn now again.
Okay, I need a coffee, but anyway, I'll try to do it.
You want a 5 minutes break for the coffee?
No, I'm joking. No, don't worry. I'm joking. Can you see my screen? I suppose.
Yes.
Can you? Okay. Okay. So the last presentation will treat about multi-risk, cascading effect analysis, and energy planning, time history, and cumulative damage. This is the title. This is another title, very ambitious. I'm not sure that I will be able in this half an hour to be exhaustive on this issue. However, I would like to fix some concept that and some approach that will clarify which are the problem of this kind of analysis. Not all the problems are completely solved, and I'm confident in the possible approach that I will propose. But anyway, we are on the track. I think that we will discuss today these issues in order to make a bit more clear in the future what could be the application of this. Starting from the result of an Espresso project that was a supporting action for the DG research that I was leading. In this project, we prepare a vision paper that is available at the address that you see in the bottom of the slide. And in this analysis, we first of all had in mind one of the main address of the DG research, that was to identify the way to merge the climate change adaptation and disaster risk reduction. This was the main goal that they want. These are two big silos of researchers. The community of disaster risk reduction and climate change adaptation, let's say the geohazard problem risk and the climate change risks are two different communities. And one of the main goals was to present the different problem that you can arise in these two different silos and how these two silos could be merged. So first of all, giving a glance to this slide, you see that there are different priorities at European and the global level. You see here that for instance, earthquake is a problem, mainly as a problem of the south of Europe. And hydrogeological events is generally a problem of North and Central Europe, for instance. And the fatalities and the people affected are differently distributed in Europe, so that actually these show how in different countries different capability for resilience and for a prompt response and research needed change according to what is basically the different impact and the different main problem that they are faced with. Here are some again some figures about at the global side loss event worldwide. This analysis has been I mean, is dated 2018. That was the time of the studies that we did. And there are some interesting links where you can see in the detail data about the main events with the casualties and the damage, and the comparison between geophysical events, meteorological events, hydrogeological events, climatological events, and what we call in one word, catastrophe. What you see here again, it's on this slide is the likelihood on the abscissa and impact on the other axis, and you see that in the red square there is the maximum probability to have the maximum impact. That is basically extreme weather events, natural disaster, cyber attacks, and failure climate change mitigation and adaptation. This is just in one glance which are the priority that we have at the European and the global side. Of course, all the action of our studies was done was taking into account all the document that has been produced by the European Commission along the years, the Sendai's framework, the Agenda of Sustainable Development of 2030, DRMKC signs on for the disaster risk mitigation 2017 reports, and so on. So all these document has been taken as background in order to analyze at the global level which are the different initiatives ongoing, which are the document to address the work, which are the operative plan that has been produced for the risk reduction and the climate change adaptation. What we provided was 5 lines that here was represented as the map of a tube. That was the contribution for the next research framework that at the time was foreseen Horizon Europe. Now we are now Horizon Europe starts, so we are in Horizon Europe actually, and you see that the line where better data for a resilient future, and here there is no time to go into detail, but there is different hazard, the quantity, quality, harmonize the data, availability, and so on. And for each of these, there are some joint points between better data for resilient future, risk governance, and partnership. overcoming the implementation gap and disaster risk reduction and climate change adaptation, human behavior, and improved risk and impact assessment. All these can be found and detailed can be read in these two documents available on the web from Espresso. One is the vision paper, and another one is the guideline. One of the main issue arisen by this research was the necessity of the multi-risk approach. This was identified 4 years ago as one of the main gaps for the evaluation of the strategies and to be taken into account for the governance of the local authorities. And actually, the future is addressed as the next X for the multi-risk assessment. Shortly in this infographic, you can have a look at what we mean for multi-risk approach. So consider in the first column that we have a data acquisition. There is this line that is time, and this is important because the time and the space, we'll see later, will play an important role in the multi-risk approach. Okay, data acquisition. Data acquisition means for earthquake, exposure, vulnerability, for different hazards that could occur, for different earthquakes, so basically that could occur. Then you could have a tsunami and different tsunami that could occur, landslide and different landslide that could occur, volcanic eruption, and so on, and many others. Besides the data acquisition, you could find the scenario analysis. Well, impact scenario analysis, as we said, is one single extraction of all the possible events that could occur for different hazards. So you can have a series of impact scenario evaluated for different hazards that contribute to the risk analysis. Of course, all the impact scenario for earthquakes contribute to the risk analysis for earthquakes. All the impact analysis of landslide or tsunami could contribute to the risk assessment of landslide or tsunami. But then this has to be put together, like in the last column, as a multi-risk analysis. Yes, it looks quite complex, of course. It looks quite complex, even if you put on top of that, that some of the events of different hazards could be put in a chain of events, like in the cascading events or cascading effect. But you see, again, we now are coming back to the terminology, because cascading event is not exactly the same that cascading effect. And then we will discuss a bit on that. Again, the two risk and scenario, we already discussed this. I don't want to go through these. Again, the terminology about hazard, exposure, vulnerability, there is no way to discuss again this. Well, I will skip this slide because this is typically what we are doing in Italy, and I don't want to spend time on that. So as the map of the unconditional damage map, percentage of building with damage greater than D1 for 2 different kind of soil. These are the results that we provide and include in the national risk assessment that the European Commission are asking to each country in Europe in order to fix a benchmark, in order to check every 2 years if they improve in the reduction of risk. Okay, these are the map for D greater than D3, and this is greater than D4. Okay, just to have an idea of which are the results for earthquakes that we produce for risk assessment. This is the medium damage for a return period of 475 years. If we compare the evaluation that we did in observed damage and by using the database of Plinius and so the observed damage and the calculated damage in L'Aquila, we found that there is a good level of agreement of damage. The same for building with the damage greater than D3, and the same with the building of damage than the D4. In this case, we did a bit what Evie was showing us when they tried to test the tool that she showed us. We did the same with our tool and with the observed damage in order to see if after the L'Aquila earthquake, to see if the results obtained by simulation were I mean, comparable with the damage observed on the site. But coming back to our discussion on the cascading effect, you see, cascading events are events that occur as a direct or indirect result of initial event. For example, if a flash flood disrupts electricity to an area and as a result of the electrical failure, a serious traffic accident involving an hazardous material spill occurs, the traffic accident is a cascading event. If a result of hazardous material spill, as neighbor must be evacuated and the local stream is contaminated, these are also cascading events. Taken together, the effect of a cascading event can be crippling to a community. This is the definition of a FEMA. I was keen to read it because we will see that our approach to cascading event, starting from this definition that obviously is shareable, I mean, is very logic, is correct, is a little different because some specification has to be done. Again, this is another definition by Pescaroli and Alexander. Cascading effects are, look, that the previous one was cascading events, okay, by FEMA. Here we are speaking of a cascading effect, are the dynamic present in disasters in which the impact of a physical event or development of initial technological or human failure generates a sequence of events, a human subsystem that result in physical, social, or economic disruption. So, in other words, in this definition is include even the fact that is not an event, just only an event that create another event. Let's consider in our field of interest that it is much more easy to understand. An earthquake that produce a landslide, okay? This is for us quite normal to think about this. But just to anticipate one of the applications that we will show later. But this landslide could create the failure of a pile of electricity. And this could create other possible effects, because in that case, we could say terminologically that earthquake and landslide are two events, but the electricity pile or system could taken at the beginning in consideration as an element at risk, because it's what we call lifelines element. Okay, so in this case, we study the vulnerability of element at risk. And if the element at risk fail, it could become a technological hazard. So it could create other kind of effects on other element at risk. So that from a chain of events, you could pass through a chain of effects, not directly, so from the event, the natural event, to impact on the element at risk, physical element at risk. But you could make this sequence passing through technological hazard that at the beginning were considered as element at risk, but then became other technological hazard. So, and in fact, in the project Snowball that we closed in 2017, we approach this kind of problem under methodological point of view, taking advantage from previous project that was Matrix. Matrix has been another project that was closed quite some years ago. We started in 2014, and Matrix was closed in 2013. But that was actually not really multi-risk, because even if in the title was defined as multi-risk, Matrix made a great job on multi-hazard assessment. So the interaction of a cascading effect in that case was not a proper appropriate terminology, because they could say interaction of cascading events in that case. Okay. But coming to the Snowball methodology, cascading events in the scientific literature, according given matrix U, is a cascade of events in a series of adverse events generated by single or different sources. So the event tree is the probabilistic approach more appropriated. So you can see here, for instance, in yellow, there is a triggering event that could generate the second events and so on, other kind of events, creating a grid. This is the simplest way to identify the sequence of event. Each of those has a probability to occur according the intensity of the previous one. So that in theory, you could have not just only one triggering event. You could have even more triggering event that could be even independent one from another, okay, that could generate event trees. I'm thinking of the volcanic eruption, for instance. The volcanic eruption is the classical event that has a series of phenomena. You can have earthquakes, but you can have tremors, not disaster earthquakes in the unrest phase. So that you cannot say that earthquakes is certainly one of the events of the chain. You could have tremors at the end, the eruption, or you could have one or more earthquakes, damaging earthquakes, before the eruption, and this could cause by itself a chain of events, because the earthquakes as a precursor of the event could create a landslide and could create other kind of effects that we discussed before. Okay, but then you could have, for instance, the ashfall, and ashfall could create other kind of series of consequence by contaminating the water, by damaging the electrical system, and so on, all the other events. So let's consider that in theory you could have many different triggering events, and for each of these triggering events you could have an event tree. But of course, an event tree of series and sequence of a consequence of cascading effect. So the snowball methodology proposes to study the cascading effect like a typical scenario analysis through the assessment of damage induced on element exposed by a single timeline of events, called the cascading scenario time history. That is the one that you see down there. Choices on the base of ad hoc criteria. For instance, probability of occurrence of time history, impact on specific element at risk, stakeholder interest. For instance, the civil protection could ask you, what happened if I should face with this sequence of events? What could be the impact scenario? And what could be the impact scenario according to the time? So according the increasing of the time history. That's why, as you see, cascading event timeline, the blue one that you at that time indicating with the arrow, will allow you to make a snapshot at a certain time of the situation, where with the snapshot of that, you could see the overlap of the impact scenario for each chain started by the different triggering event. To do that is snowball. You should know, obviously, all the uncertainties connected to the cascading event. And so to do that, two methods have been adopted. One is the classical Bayesian methods, and the other one is the elicitation techniques. I don't know how many of you are confident on the elicitation techniques by Cook. That is a mathematician. Elicitation techniques is a techniques that when you don't know anything about, you put around the table experts of different level of knowledge about that. So a young researcher, a PhD student, an old professor that is very opinionated, and a researcher in the midway of his career, and so on. And you make a test in order to evaluate which model of probability is the best according the person. An old professor is very much opinionated, so it's like a Dirac delta. You see, it's very narrow. There is no much spread out in you see, in confidence. Okay, it's a very strict confidence. The deviation is very strict. While, for instance, a PhD student has he has an opinion, that is the medium range, but as you see, is like a Gaussian curve or normal. Anyway, then you ask them some specific question on the issue that you don't know anything about, and then with the procedure, mathematician procedure, you will find which is the best curve that approximates that in uncertainty. Of course, this timeline could be affected by decision in phase of preparedness or during the emergency taken by the civil protection, because according to the decision, obviously change everything. This is an example of a volcanic eruption, as I was saying before, earthquake and ashfall. And there is the cascading event timeline and phase or preparedness and or human behavior that could affect the final impact, of course, because people can be evacuated, can escape. There are a lot of decisions that can be taken by civil protection or directly, spontaneously by population. Okay, again, so always this kind of things is well known. So let me skip these. Okay. In order to work to this kind of analysis, you need to build up what we call elementary brick. Hazards, tool, exposure, tool, vulnerability, tool, dynamic vulnerability, because you understand that multi-risk and cascading effect, an event effect actually, require dynamic vulnerability. If you want to evaluate at a certain level at the snapshot of the situation along a time history of events, you need a dynamic vulnerability tool, because if a building has been already kicked and damaged by an earthquake, if he performed another earthquake, so obviously he does not respond as after the first earthquake. He obviously is weaker. And so if ashfall come, and so if pyroclastic arrive, or LAR, or bombs, or whatever. Okay. Then against the final damage has to be as a final input that consider time and spatial distribution of damage induced on each element exposed by cascading event. So that, as you see in the top of the slide, there is the space variable and time variable that has an important role all over the analysis. And in the bottom part is clarified that the human behavior influence the final factor. Okay, here you can see one flowchart of the conceptual flowchart of the model, where in the previous column here you have the single elementary brick that produce the impact analysis. This is modified and influenced by human behavior and by the decision of the stakeholders, I would say, of this mainly of the civil protection, but not only, and of course by the social data mining that could influence this result. This goes in the impact model software module, and the output will be the damage scenario simulation, that is the snapshot of the damage at a certain level of the time history that we decide to evaluate. Finally, multi-criterion analysis could help to decision maker for the action to take into account. About space, the brick, the space, I want just to underline how is complex this analysis, because what you see the difference between these two these two boxes. In the left one, you have that there is a triggering event, that a local event, or national event, or international event that could be analyzed within a spatial domain that is the same. Okay, but this is not always. Sometimes the space influence is different. For instance, for different hazard, have a different spatial domain, and sometimes different hazard could kick the same spatial domain or different spatial domain. Let, for instance, consider the ashfall. The ashfall will, coming from the event of a volcano, will kick the proximal area a series of elements at risk, like the buildings around the volcano. And we consider that here we have more than 50,000 buildings around the Vesuvius, in the belt around the Vesuvius, that could be kicked by a series of earthquakes as a precursor event before the eruption. Then come the ashfall. Okay, that it's increased as another action the damage of the buildings, and not only on the buildings, but on the roads and humans and whatever. But there is the distal area, for instance, outside what we call the red zone, that is the proximal area where the pyroclastic flow are expected. And we call about area not farther than 10 kilometers or 15 kilometers, that will be kicked by ashfall. So in this case, for instance, ashfall will kick the building outside the red zone as the unique action on the buildings, while in the proximal area you have to consider other kind of action. So the space is evident that is important to evaluate. So as the time, because the time could be very short, like an earthquake, or could be long, like an ashfall that could last hours, even 12 hours, or like a pyroclastic flow that is again short, but not so short as an earthquake. It could last 20 minutes. And so the point of overlap the evaluation of damage by considering the time in which this event, so the arrival of this event and the last of this event, obviously make a difference in the evaluation. So has the preparedness phase, as I mentioned before, so the decision that could influence the potential cascade are very important. After the first earthquake, we evacuate everybody. Okay, so all the other will not give damage to population, or we'll keep on going and we wait for what's going on, and we will perform the second earthquakes. And so the difference in the impact will be different, and so on. So the decision taken along the series of events that we have put in a history, in the time history, obviously make the difference. Make the difference on the cumulative damage, because the cumulative damage, when arrived, for instance, the first triggering hazard event will create at the time t0 with the vulnerability a certain time of damage, a certain level of damage. Okay, this damage has to be split in building collapse, lost, as we say, and building that has been damaged but is still there, that has some residual capability to respond. Okay, and so you, in the cell of the minimum unit of research, you have to adjust the distribution. This adjustment could be done even in some shift of the class of vulnerability. For instance, if you had a very strong class of vulnerability, D, for instance, after the first earthquake, some part of the D will become C or B, so weaker. and some parts are collapsed. So you have to eliminate the collapsed, and the remnant, the building remain there, could be rearranged, and so on for all the other event, obviously using the appropriate vulnerability curves of damage of a probability matrix. Okay, up to the end of the sequence. Okay, that will provide the final cumulative damage on the element exposure and kicked by more hazard. This is vulnerability class in the case of earthquakes, and the scheme of the damage already described before, synthetically shown in the upper part of the slide. First earthquake, second earthquake, and so on, third earthquake, and so on. This is again described the dynamic vulnerability in the more and more clear way. So you have a distribution. Look, these you have a distribution. The 0, D1 remain with the same vulnerability curves because the building remain in this class. D1 is shift on one class, D3 of two class, D4 and D5 are lost and so eliminated, and so on in the sequence up to the final damage. Okay. Of course, the preparedness action in the simulation gave some other important element of variation of the analysis, because you can take a decision at long term and in the short term. Short term, population evacuation. In the long term, building retrofitting, critical infrastructure, service networking retrofitting. But of course, in the long term is something that you have to do years before, long time before. So this is part of the preparedness. That means that this kind of analysis is useful to the civil protection and the decision maker to prepare program of mitigation. This is Santorini. In the snowball, we made an analysis of Santorini using the different elementary brick in order to apply to Santorini this model. What you see here is the general framework and the customization need. The general framework means that what you see in this table is not readable, but this is just to show the logic. You see all the possible compatible link between the events. That's to reduce the combination, because not all the event could provide all the other events. Okay, so heavy rain could not determine an earthquake or a volcanic eruption. Okay, so there are some events, some combinations that are impossible, or we consider, but we assume impossible. That means, and then there is some customization of the area, because, for instance, in some area there could not be a volcanoes, for instance, or could be not a seismic area, or there could not be landslide because it's completely flat area, and so on. So starting from eliminating the impossible combination, then you continue to reducing the complexity of the problem by customizing the compatibility on the site that you want to study between a natural and technological hazard. And of course, you could define in red, yellow, and green what are the data available, the study available, and what is not. Because, as I said before, the probability of transition probability from an hazard to another is not always known. So in some cases, you have made assumption by the technique of elicitation that I showed you before. And again, another important work that can be done to reduce the complexity since the beginning of the analysis is the reducing of the element at risk, because again, not all the elements at risk are impacted by all the events. And so in this case, you could avoid the combination where elements at risk are not connected with other elements at risk, and even in analyzing which are the elements at risk that you can see or you are interested in evaluating in that particular area. Okay, so there is this general refinement from the general model to the local model. Local exposure and hazard identification, availability of inventory data, availability of vulnerability model, availability of impact model, specific requests from decision maker. These allow you to make some event tree refinement derived from the local compatibility matrix, reducing a lot the complexity of the problem. And what you see here is the customization that we did for Santorini. First of all, the hazard characterization, earthquakes and ashfall, and then the element at risk identification, exposure and vulnerability. We made a great campaign, an extensive campaign of identification of building typology and collection of data on Santorini. And then we make a database on inventory data about the population through even the census data for all the different municipalities in Santorini. We evaluate the variation between winter and summer about the population. Santorini has 10 times the population in the summer. You know very well because you are Greeks, Greeks. So you know it passed through 13,000 to 130,000, something like that, people. And we evaluate the inventory of the power grid. The time is finished, so I'll try to go. But I started some minutes late, if I'm not wrong. Anyway, I go quickly to the end. General framework and customization needs. In Santorini, there is a great problem of landslide, rockfall, and this was the main problem that we took in consideration, that the vulnerability of the services like electricity could fail after landslide produced by earthquake as a precursor of a possible eruption, and these fail the electricity and fail the power plant, so that Santorini could remain without electricity and without water as well. The power plant also, because the ash could affect the oil filters of the power plant, that is an engine, and so all the critical infrastructure as the desalinization of the water that gives the drinkable water to the isle could fail. So a real important chain of cascading event plus cascading effect, because in the middle there is an important technological hazard that will produce. This is an example of Vesuvius. At Vesuvius analysis, we evaluate the indice di rischio, the risk index, according to the prevalent direction of the wind that is in the stratosphere towards east. And so there is an high risk that all these buildings on the east of Vesuvius could fail with very high probability for the ashfall. could happen in a very short time. This was a study that the civil protection asked us to do. You see that after 3 hours, we could have the 25% of the roof already collapsed. And after 6 hours, the 60% collapses in this area. These encourage the civil protection to take the decision to increase the red zone of evacuation, in order to be evacuated before the eruption. So if before we had 550,000 people to be evacuated in the red zone 1, that was the area where the pyroclastic flow are expected. Pyroclastic flow is something that you cannot stand, obviously, so you have to escape before. They decided to enlarge with other 300,000 people to be evacuated in the red zone 2, that is this one on the east part, because of the collapse of the 60–70% of the roof in this area because of ashfall in the first hours. Okay, and this was done. Thank you for attention. I'm sorry if I've been a bit longer.
No, it was very interesting. Very interesting. So we are about 4 o'clock. It seems that we do not have a lot of time for discussion. Am I right, Petros?
We could allow 5–10 minutes if there are some questions. Otherwise,
yes,
I'm sure we are going to get a chance to discuss this in other times also. I mean, it's so much information in such a short time. So
yes. I would like also to ask a lot of things to Giulio, but I think that it would be better to discuss it in a more face-to-face or
yes, a lot of things today has been said. Really interesting.
Yes.
Yeah, I remain always astonished of how much work is done around the world, and you don't know that is there. I mean,
So is there any question or something that someone would like to raise as important issue for the discussion or for clarification or whatever?
I think there were some questions with regards to information that was provided during the presentations. And I don't know, we are going to have to see how we can, if we want first, and then how we can disseminate it. So maybe we can ask the people who are interested in this to contact us and see how we can communicate some of this information, because the volume is too high, so it's not easy to just post maybe on a web page or just send it through emails. So if someone is interested, maybe it's easier to communicate with us and then we can disseminate.
Yes, there are already
some
questions. There are already some questions and answers in the chat. But I think that everybody could send these questions to the presenters, and I suppose that he or she will get the answer.
I think that the main goal of this virtual training was to give a glance to all to some of the potential topics that could be taken into account by the PhD students, by the project, that could be as much as exhaustive as possible in the naming the different aspects to be considered, but we do not pretend to be exhaustive in the presentation of these topics, of course.
It was,
So
yes,
because are very complex and very, I mean, it required, I mean, other opportunities as a I'm not able to pronounce your name, Pitilakis. Yeah, really, anytime, I know you since 20 years, but anytime I remain, that is Kyriazis.
Yes.
Kyriazis, yes. I'm sorry for that. But anyway, as Kyriazis was saying, I think that there could be other opportunities. There must be other opportunity, longer time to discuss, you see, one-to-one, these kind of things.
We do have our next virtual training coming up, so we could maybe try and accommodate maybe smaller volumes of information and making maybe in a larger detail. I don't know if that would be useful, let's say.
Yeah,
but we can discuss this and make a decision in time.
As Kyriazis was saying, the easiest way is to put the reference and to collect all the, I mean, not all, but the main papers that describe what we have discussed today and what we will discuss in the future virtual training.
Yes.
This is a good base, I mean, to start.
And for a researcher and a PhD candidate, yes, this is what he has to get and to work on it and with it. It's the way to be done. If there are no other questions, I would just like not to give me, Giulio, an answer, but just comment on this. In all your methodologies, I see that practically you are based on a kind of proposing indexes in order to give a certain hierarchy. Is there a certain methodology, a unique methodology that you follow, or it is based on multi-criteria and multi?
Exactly.
And subjective, I mean.
Yeah. The index come out when you work on multi-criterion analysis, because the index, in a way, is one of the only way to put together different evaluation, trying to define one single parameters that could give an idea of the prioritization of the choice for the civil protection. But generally is more addressed by the convenience of the stakeholders than by a methodological choice. You see what I mean?
Yes. Yes, this is the problem that we face always when we are trying to give a certain grade, 1, 2, 3, 4, 5, how we define and on which basis we are. This is.
I know the problem, but since there is so much things included in the analysis that you do, that is not so easy to transfer these to the decision maker. They don't want to know all this problem that we have. They want just simple parameters that assess priority in the decision. And of course, they give you which are the criteria that they want to follow. But then they expect as a return a simple parameterization of this criteria.
Yes, I see. And finally, what you are providing is a certain hierarchy of the losses or the hazard or the risk, etc., saying that this is worse than the other.
That's right.
This can be done, and on this, then the adaptation and decision making could be done in a more rational way. I mean.
Yeah.
Okay.
Yeah.
Okay, I think that we are all quite tired, especially the
No, Evie was really good.
Oh, she's
Really
very
good.
good, no problem.
She's brilliant. She's really brilliant. Okay.
Okay, so Petros, I invite you to close this virtual training meeting as coordinator.
Well, I just want to say that today was so obvious that we are so fortunate that we participate in this project, because it is obvious how much work is being done through the years, and for us it's a good opportunity to have mentors and people who are actually working with us or guiding us, and it's also a good challenge for us, a big challenge for us to see how much we can absorb and how much we can use in creating collaborations with you, and maybe assisting in ways of getting on or jumping on this train and see how far we can get, and maybe transfer some of this knowledge and all these results in Cyprus. So at least there is some benefit also for Cyprus from this project. So we are very grateful for that, and of course we want to thank you for spending the time. I mean, everybody I know have other things to do and a lot of things to worry about, but that was very useful, and thank you for that.
Okay, now you have to prepare the April 7th meeting.
Yes.
Okay.
Unfortunately, yes, we have to do it and the time is closing very fast.
Try to answer as fast as possible to the questions that Evie is.
Yes, I am actually compiling this technical report. It's just I don't have this stretch of time, and there's always something else happening. And then I will forward it so everybody can comment or add or something. So hopefully I will be able to do it before Tuesday when we have this meeting in Italy. So hopefully by then we're going to have more to say.
Kyriazis, next week they are here. You see, they are ready. Boom, 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 boom.
Yes, well, that's the problem when you have more than one person doing things. So
okay, send all this as soon as possible, because
yes.
Is very...
We have to, because otherwise we are going to run out of time. So
okay,
Giulio, did you want to maybe I can send you a link?
I can stay.
You wanted to ask me some things, because Evie is organizing this Zoom. I can send you another one right after we hang up.
Okay, in 5 minutes I call Mattia and we will arrange the program for next week here. Okay.
Yes. Okay.
Okay.
Ciao.
Bye-bye. Thank you very
Thank you,
much.
everyone.
Bye-bye.
Bye.
Bye.
Bye-bye.